Okay, good morning to everyone. Yes. So, good morning to everyone. Hope everybody is doing good. So, I hope I have asked you to solve some questions of the classroom practice questions. So, yesterday we solved some previous GATE questions and previous IS questions. So, I hope you understood how to solve those questions, and I have shared that PDF also with you. So, and I have asked you to solve question number 2, 4, 5, 6 from the classroom practice questions. I hope you have solved those questions. So now, today, we are going to discuss about, yes, assignment has not given, see that, today, as we'll complete with this chapter number 9, I'll be giving you chapter number 7, 8, 9, these 3 chapters assignment. So we'll be seeing that assignment today. So don't worry about that. I'll give the 3 chapters assignment today only. Okay, fine. So now, I'll provide you chapter number 6 assignment solutions today, and I'll be giving assignment for the chapter number 7, 8, 9. Okay, let's talk. Okay, so now let's start our session. So yesterday I discussed about the flow net. So for a moment, let's go for the yesterday's class. For a moment, everybody please look over here. So we have been discussed yesterday the seepage analysis, and in the seepage analysis, I explained you that Laplace equation is going to be used. And earlier we took the Laplace equation for the isotropic soil, and we have made some characteristics of the flow net. And with that flow net, you know that through any flow channel, discharge remains same, and between any two equipotential lines, head drop also remain same. So by using these characteristics, we have done some applications, and the most important application is Q is equals to K into H into NF by ND. So now, in the case of this seepage pressure, wherever you want to find out the seepage head, there total seepage head minus head loss up to that point, and pressure head. How to find out the pressure head? You know it very well. And how to find out the exit gradient? I exit. Now, coming to the anisotropic soil, in the case of the anisotropic soil, you cannot apply the flow net properties directly. You have to convert that flow net into, means you have to convert the anisotropic into equivalent isotropic nature. How you are going to convert that anisotropic to equivalent isotropic is by reducing the base length of the dam from x to x dash using a reduction coefficient ky by kx. Once we reduce, now you see this is the actual figure in the field. Now, while you are plotting, we are going to plot with B, and then we are going to draw the flow net. See, once you transformed, then only we plot the flow net. After plotting the flow net, then you can find out the NF and ND. And what is the discharge passing over here is nothing but KE into H into NF by ND, where KE is equals to root of KX into KY. So these are the things that we have been discussed in yesterday's class. So now, Mr. CVR.ac.in, that a water filled model in excavation is nothing but a heaving model. So you please go through that. Once you go through that, whatever the model it is, it's just simply the total downward is equals to total upward on Mr. CVR.ac.in. I'll explain fifth question. Don't worry. So you told that you will upload a GT handwritten notes of 13 papers. Please upload it. I'll upload. I was having some other works apart from this one. Some academic works were there. So I was busy with that. So I did not got a time to upload, but definitely I'll upload today. I have to see because I have been prepared it long back. So I'll be seeing where it is and then I'll share that also. Okay, so now let's go to this. Today we'll be discussing about the Earth Dam. Today we'll be discussing about Earth Dam. See, so far we have been discussed about the gravity dam, right? So now we are going to discuss about the Earth Dam. So this is a hydraulic structure constructed with a fill or a soil mass. So how does this Earth Dam is going to be present? And how does the seepage is going to be passing through the Earth Dam? And how to find out all the applications? Now let's see. You see, this is an Earth Dam. Which is having an impervious strata like this. So it is having an impervious strata like this. And whatever here, this is upstream water level. And whatever here, this is a downstream water level. So upstream water level and downstream water level. See, this is upstream water level and here is going to be downstream water level. So now you see, this is nothing but an earth dam and this earth dam is made up of a soil mass. So this soil must be having some coefficient of permeability K. So now in the case of the earth dam, when the flow is going to be happen, the flow is going to be happen beneath the dam or through the dam. This is an impervious stratum, Nana. There is an impervious stratum. So impervious strata. Now, if I want to find out all the flow net characteristics, means flow net applications, first of all, I have to draw the flow net. How to draw the flow net, sir? So you know that along the direction of flow, there is a flow net. So now you see, can I say this is a water table and this is a water table and in between the flow is going to be happen. So now simply you draw a smooth curve that joining the upstream water level and downstream water level because the flow is going to be starts to pass through the dam or not. So here there is a flow through the dam. So now when there is a flow, then there must be the flow lines are not. So now what are those flow lines? Those flow lines, you see, this is the topmost flow line. Observe, this is the topmost flow line. And so what is the meaning of this topmost flow line, sir? Which means, does this exactly acts like a water surface or not? Yes. So now you see, means I wrote over here, this is a soil mass And if you observe, when the flow is going to be takes place along the direction of flow, if we draw a line, that is known as flow line. And this is known as a topmost flow line or not. So now my question for you, is there any flow happening above the topmost flow line? No. And this topmost flow line is known as a phreatic line. What do we call? Phreatic line. So now it is known as phreatic line. So what is phreatic line, sir? Phreatic line means topmost flow line. So phreatic line means topmost flow line. And how does the shape of this flow line looks like? Shape is parabola. The shape of the phreatic line is going to be parabola shape, Nana. And below phreatic line, soil is fully saturated and above either capillary saturated, means depending upon the soil mass, just like you know that, right? Groundwater table, below groundwater table soil is fully saturated, and above groundwater table you know that soil is either partially saturated or capillary saturated. Partially saturated or dry. So but you know that below the soil is going to be completely saturated, and this is the line which separates the full saturation to partially saturation or capillary saturation. Just simply it will acts like a groundwater table. Simply it acts like a groundwater table. So now here pressure head HP is equals to 0. Because you know that there is nothing but a water table or not. At the water table, the pressure head is going to be 0. See, I am telling you at this point, at the phreatic line, or I'll write this. At phreatic line, pressure head HP is equals to 0. Then total head is equals to pressure head plus datum head. When pressure head is equals to 0, then total head is equals to datum head. So these are the silent features of the topmost flow line. See, once we know the flow line, once we know the flow line, now we can draw the remaining flow lines. This is the topmost flow line. So now if you observe, these are the other flow lines I'm going to draw. There is one more flow line. So now, how many flow lines are there here? 2 flow lines are there here. So now, I can draw one more thing, but I don't want to inject any difficulty over here. So whatever, this is nothing but the flow lines. So now you see, how many number of flow channels are there? Can you please tell me how many number of flow channels are there? How many number of flow channels are there? Please let me know in the comment section. How many number of flow channels are there? I'm asking you flow channels. Okay, fine. There are two flow channels over here. A lot of people are saying 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 1. So the answer is 2. The answer is 2. Why, sir? Sir, can you see any flow happening above this flow line, sir? Can you see any flow happening here? No. There is no flow here. I told you below phreatic line soil is fully saturated, right? So which means above phreatic line there is no flow. Now the flow is going to be happen in these two channels only. Now the flow is going to happen in these two channels only. So how many number of flow channels are there here is nothing but 2. How many number of flow lines would be there here? 3. How, sir? Sir, I have drawn this one. This is a first flow line. This is a second flow line. And this is going to be the third flow line. The impervious strata is going to be acts like a flow line. So now here, impervious strata acts as default flow line. So now, how many number of flow lines are here? Means how many number of flow channels are there here? So this is one flow channel and this is the other flow channel, which means NF is equals to 2. Which means NF is equals to 2. So now you tell me here, look, everybody, see this is a flow line and this is also going to be a flow line. And this flow line, see, for this one, this is going to be perpendicular or not? Yes. So if this is the flow and this is a perpendicular line. So now you tell me whatever the line perpendicular to flow line is nothing but equipotential line or not. So if this is a flow line, then definitely this is going to be the equipotential line. So whatever this is nothing but equipotential line, which means can I write upstream and downstream face of earth dam acts as equipotential lines. Acts as equipotential lines. So now, once you know that is going to be equipotential line, you please draw it. Okay. So now, once we know this is going to be the equipotential line, so wherever there is a possibility, draw the equipotential line perpendicular to the flow. So now, you see over here, yes, these are going to be the equipotential lines. These are going to be the equipotential lines. So now, how many number of drops are there? Please tell me here. How many number of drops are there? 1, 2, 3, 4, 5, 6. So 6 drops are there, or I can write you. This is the 6th drop, right? This is the 6th drop. So 1, 2, 3, 4, 5, 6. 6 drops are there. So total number of drops are going to be ND is equals to 6. See, this is the 6th one. That's the reason why I represent as a 6 over here. So now you observe over here. If you see, whatever the number of drops are going to be 6. So once we know this one, then we know the difference between the water levels as H, and the soil must be having some coefficient of permeability K. So now I have drawn the flow net. Once I draw the flow net, can't I find out the discharge? So then the seepage loss rate, Q is equals to K into H into NF by ND. That's it. There is no change. The equations that we have seen is same yesterday and today. But you see, what is the new points that I was saying over here is, whatever the topmost flow line I am drawing you, that is nothing but the phreatic line. The topmost flow line is going to be the phreatic line. So these are the silent features of the phreatic line. Now, if you see the topmost flow line is a phreatic line, and you see at this water table, do you think at water table, what is pressure? At water table, the pressure is going to be 0. So you know that at water table, if you insert a piezometer, does water level rises over here? No. So at water table, the pressure is going to be 0. So that's it, the seepage loss rate. And similarly, if I want to find out the seepage pressure, what is seepage pressure? Let's say I want to find out a seepage pressure at A. At A. What is the seepage pressure? Gamma W into Hs of A. So you know that flow is going to be starts with the what head? H. And when it moves to point A, it loses some amount of head. So Hs of A is nothing but total seepage head minus head loss up to A. And how to find out head loss up to A? Head loss up to A means simply nothing but how many number of drops? 1, 2, 3. 3 drops are there. 3 drops are there. N into delta H. So this is the condition where delta H is nothing but total head drops by ND, where N is number of drops up to A. See, these are the things that we know it very earlier. We know these things. Now, I'm asking you to find out these things. But in the case of earth dam, there is no uplift pressure. In earth dam, there is no uplift pressure. So these are the things that you need to know in the case of the earth dam. Now let's see what are the type of failure you can see in the case of earth dam also. Sir, can we draw any number of equipotential lines? No, it depends upon the boundaries, but I am not here to explain you the construction of the flow net. I am explaining you the elaboration of the flow net, understanding of the flow net. So here it can be 6 equipotential lines or 7 equipotential lines, but I am taking you some example. If this is the flow net, then how many number of drops are there here? Sir, here soil is isotropic or anisotropic? See, if it is anisotropic, I would have mentioned, right? And even if it is going to be anisotropic, you know what to do. You reduce the base dimension. That's it. When you reduce the base dimension, the equation is going to be same. Q is equals to K. Sir, where we can see the practical live earth dam? There are a lot of live earth dams. You please Google it. You will get to know that. No, earlier days the dams were earth dams only because earlier days before the concrete technology, we used to construct bulky sections, which means the big sections we used to construct. So because of that, the cost is also going to be more. Earlier days, almost all the dams are going to be earth dams. But from 19th century onwards, we are constructing the dams from 18th century. Yes, not 18th century onwards, we are constructing the dams in the case of concrete or gravity dams. So you please go through the Google, you will get to know that. Sir, why flow does not take place above the flow line, sir? Please insert your mind over here, sir. You see this one, sir. How come the flow will be taking place, sir? Flow takes place from higher water level to lower water table, sir. So this is the higher water table and this is lower water table, sir. Flow will be taking place from higher to lower, sir. So this Laplace equation is used in problems. See, Laplace equation is not used in problems, but Laplace, from the Laplace equation only we have been derived everything. On what basis we are fixing the flow lines? We are fixing the flow lines on the basis of boundaries, impervious strata, exit gradient in earth dam, sir. Exit gradient in earth dam, sir. You please tell me, sir, what is the exit gradient in earth dam? You please come on. If you explain, I exit is equals to delta H by delta L at exit. You see, this flow field is there or not? Exit, whatever I am showing you, this is going to be the exit field. So you know that they will provide you the length of the exit. This is delta L at exit. So they will provide you that. Then you can find out the I exit. Okay, fine. Sir, is phreatic line considered as HGL? Yes, because the phreatic line and HGL. HGL means hydraulic gradient line. Both represents the water surface only. Okay, fine. So, foundations are pervious. I hope we can draw flow net. Do you want much more complexity into your pocket? Do you want much more complexity into your pocket? If there is a flow above and below, is it easy for you to analyze that? Type of questions. Can we find effective stress in this case? Yes, but we don't need to. They are not asking to find out any effective stress. Okay, now the failure piping failure in earth dam. So how to so now coming to the piping failure in the earth dam. In the case of the earth dam, so now again So if this is an earth dam, now everybody have a look. See, when you are going to draw the flow net, what happens over here is, if you observe, you know this is a topmost plane, yes or no? And you know when the flow is going to be passes the discharge. See, throughout this, we assumed flow is steady, which means the discharge is going to be same. But now, everyone, you please tell me, this is the cross-section area over here, yes or no? Now, when the flow is going to be happen over here, at this point, the cross-section area is going to be less, yes or no? When the cross-section is going to be area is going to be less, can I say, at the toe of an atram or on the downstream side, when the area is going to be less, you know that from the continuity equation, Q is equals to A into V. When area is going to be less, velocity is going to be more or not? Yes. So, in the case of the atram, on the toe, due to seepage velocity, due to high seepage velocity, what happens is more seepage velocity will cause the particles to erode. When the particles are going to be eroded, now this erosion, you see, now. So from this point, what happens over here is, have you remembered the piping failure? Yes. So in the case of the piping failure, there the soil erosion is due to upward seepage. Here it is not due to upward seepage. Here is due to more seepage velocity, on the downstream side, due to more seepage velocity on downstream side, soil erosion will occur. So from here onwards, the soil is going to be starts to erode. Here onwards, the soil is going to be starts to erode. So when the soil is going to be starts to erode, it will move towards the upstream or not? Yes or no? So whatever this is nothing but here, this is known as soil erosion. So what I want to convey over here, in the case of the atram, as you go, the flow area is going to be decreases. See, this is the flow area here. And by the time it comes, this is the flow area. By the time it comes, this is the flow area. Yes or no? As the flow area is going to be decreases, the velocity of the flow will be increases. So what is the actual velocity of flow? Seepage velocity. By the time it reaches the toe, the velocity of the flow is going to be more, then the soil erosion will occur on downstream side and progress towards upstream. So what is the preventive measure then, sir? The preventive measure is by providing a graded filter. By providing graded R2 filter. So now, if I provide a graded R2 filter, now you see what is going to be happen over here. The same figure. So now this is going to be the graded filter over here, and as you know, this is impervious in strata. This is impervious. Flow will not take place beneath this one. This is impervious, and this is going to be gravel, and we call this one as a toe filter or graded filter. We call this one as toe filter or graded filter. So then what is going to be happen, sir, if you provide this one? See, now this is going to be pervious in nature or not? Yes. So you know this level is going to be, this level is a upstream water level. So now how come the flow is going to be happen here, and this is going to be the downstream water level, upstream water level and downstream water level. So now how come the flow is going to be happen over here is, so there is upstream and here is going to be downstream. Now you observe the flow starts from this point only, but you see the biggest difference here is, here there is no filter, which means this entire is going to be impervious strata. Then the flow will be ending at the downstream phase only. Yes. Now if I provide a toe filter or a graded filter, now the flow will pass us up to this point, fine. But now it won't move to the downstream phase because the graded filter permeability is more. When the graded filter permeability is more, water will seeps into the soil mass whose permeability is going to be more. Yes or no? So now instead of this one, what happens over here is, this level will be directly enters into here. Now this is going to be the topmost flow line. So in this case here, this is going to be phreatic line. Phreatic line. So now if this is the phreatic line, the remaining things are going to be the phreatic lines. Means if you know this one, then you can draw the remaining things also. I hope you understood this meaning over here. So by providing the graded filter, what happens over here is the flow line will touch us over here, so that the water will seeps over here through this. Then the water goes to the downstream side. So here you don't need to worry about any other thing. There is no failure of the soil because gravel size is more, so soil erosion will not occur easily, and its permeability is going to be more. It will allow the water easily. So no soil erosion and water escapes easily. I told you in piping failure also, we provided filter for allowing of the water and not to escape the soil particles. So I hope you understood the difference over here. So this is the preventive measure, and when you provide a preventive measure, what happens? The phreatic line is going to be changes to the downstream phase, from the downstream phase to the gravel, so that the downstream is going to be safe from the soil erosion. So now this phreatic line, what is the shape of the phreatic line? What is the shape of the phreatic line? The shape of the phreatic line is going to be parabola. The shape of the phreatic line is going to be parabola. So from, there is a one more equation. There is a one more equation from Koznitz. From Koznitz, in the case of earth dam, in earth dams, from Koznitz, Q can be find out K into S, where S is known as focal distance. Where S is known as focal distance. Sir, how to find out this focal distance, sir? Now you observe. Can't you see anything that I am writing over here? Are you able to see or not? Okay. So now let's see this one. Okay, fine. Yes, I did not write anything in that box. Okay, fine. Now you see this box from the properties of parabola. So I can write from properties of parabola. Now you see in this case, if this is a parabola, you know the parabola, right? If this is a parabola, then there is a directrix over here. This is a directrix. So this is a parabola. From the properties of the parabola, and for every parabola, you know that there is a one point known as a focal point, where f is a focal point, and from the focal point to the directrix, whatever the distance is nothing but focal distance s, where s is focal distance, where s is focal distance. Now you observe from the properties of parabola, the property of parabola is you take any point on the parabola, see, let's take this point is P of x comma y. You take any point on the parabola x comma y. So now if you observe whatever the point from this, you see whatever the distance from the focal point, to the point on the parabola, to the distance from the point on the parabola to the directrix, both are going to be same. So what I want to say here is any point on the parabola, let's say P. So whatever this distance FP and PD, both are going to be same. This is a property of the parabola. The property of the parabola is whatever the distance from the focal point to any point on the parabola is equals to distance, horizontal distance from that point to the directrix. So FP is equals to PD. Do not ask me, sir, how it is going to be equal. That's a property of the parabola, Nana. For that, you have to go for your basic mathematics. So don't ask me, sir, what is directrix and how you are going to prove the FP is equals to PD. That's a property of the parabola. I'm telling you from properties of the parabola. So now, where FP is equals to PD. What is this FP, sir? You observe. If you see, this is x and this is y. Because I am taking this point as x comma y or not. When I take the point as x comma y, then what is FP? What is FP? If this is x and this is y, then what is FP? FP is equals to root of x square plus y square. So root of x square plus y square is equals to what is PD? What is PD over here? You please observe. The PD is equals to x plus s. X plus s. So from this, s is equals to root of x square plus y square minus x. This is how we need to find out the focal distance, where s is equals to focal distance. They will mention you the x value and y value. Now you see, in the case of the dam, wherever the intersection of impervious to filter is focal point. Intersection of the impervious strata to filter is going to be taken as focal point. If that is the focal point, then this is the directrix. This is the directrix, and this is going to be the focal point. And whatever the distance from the focal point to the directrix, this is going to be the S. So what is this S? S is going to be focal distance. And how to find out the Q value? Q is equals to K into S, where S is going to be the focal distance, and this focal distance is going to be find out root of x square plus y square minus x. You take any point on the parabola, you can find out the focal distance. So how to find out this one? That's the construction of the earth dam that we will be seeing in IES conventional. Do not go beyond this for gate examination. For gate examination, they cannot ask beyond this one. In the case of IES conventional, I'm telling you for conventional purpose for IES people. So there is something extra topic of this earth dams. So that we will be discussing in the later classes. For the mains classes, not now. That's all with the gravity dams, earth dams. In the case of earth dam, how to determine the discharge and how to determine means piping failure, what is a preventive measure, and what is the other formula from the property. This is from the properties of parabola given by the Koznis. So what is Q? Q is equals to K into S. Drainage gallery is different. Drainage gallery is going to be provided inside of the gravity dam also to collect the drainage means so I hope you have understood these things. Now, the last topic in this chapter. With this, I will be concluding this chapter. In anisotropic soil, once again, I should have explained this topic yesterday itself, but I couldn't explain. Anisotropic soil masses. So now let's take this is an interface of two soils. Interface between two soils. Let's take soil 1. Let's take soil 2. Soil 1 permeability is K1. Soil 2 permeability is K2. So now my question for you. Here is, see, this focal point is taken as wherever there is an intersection between the impervious and gravel, this focal point is going to be, this intersection point is going to be focal point, and the distance from the focal point to the directrix, the distance is going to be the focal distance. Yes. How to determine that S is going to be from properties of parabola? You please don't focus more for this one. So now if it is going to be soil 1 and if it is going to be soil 2, soil 1 permeability is K1, soil 2 permeability is going to be K2. Now, let's say if the flow is passing from soil 1 to soil 2, from soil 1 to soil 2. So, let's see. The flow is passing like this. Let's see the flow is passing like this. Let's take this is a flow line. Let's take this is a flow line. So now everybody, you please tell me, see what is the permeability here? K1. And what about the permeability here? K2. Different permeabilities means once the flow is going to be enters from soil 1 to soil 2, do you think the flow line is going to be same, or do you think the flow is going to get deviated? Definitely flow gets deviated or not? Yes or no? So definitely the flow is going to be gets deviated, because when the flow is going to be takes place between two different soils, the flow line gets deviated. When flow occurs from or between two different soils, flow line get deviated. When the flow lines gets deviated, now it is not going to be the actual flow line. It is not going to be the actual flow line. So now the actual flow line is going to be looks like the actual flow line somewhat looks like this one. So this is going to be the flow line. Now let me draw a normal to the interface. Let me draw a normal. This is the interface, right? For this normal, what is meant by normal? Normal means perpendicular to the interface. This is normal to interface. I told you the entire flow net does not depend upon the soil property. Here the deviation would be there. The small deviation would be there. That does not changes the entire things. Okay, the discharge and all those things. See, I told you the flow net. Flow net is a combination of flow lines and equipotential lines. But when there is a change in the permeability, what happens over here is that the flow lines get deviated. For example, 10 flow lines you want to draw, you can draw 10 flow lines. The number of flow channels does not depend upon deviation. How many number of flow lines between that space is known as flow channel. So now you see whatever the angle made by this flow line with this normal, let's take it as alpha 1, and by this flow line means this is the deflecting flow line, right? By this angle, this is going to be alpha 2, where alpha 1 comma alpha 2 are deflection angles. Deflection angles. So if these are going to be the deflection angles, there is a proof for this one. You don't need to provide the proof, and that deflection depends on permeability of soil. Permeability of soil as K directly proportional to tan alpha. K directly proportional. See, this is not alpha, this is a directly proportionality. K directly proportional to tan alpha. K1 by K2 is equals to tan alpha 1 by tan alpha 2. K1 by K2 is equals to tan alpha 1 by tan alpha 2. So, which means you observe over here, if I say K1 is more than K2, if I say K1 is more than K2, if K1 is greater than K2, then alpha 2 is less than alpha 1. Yes or no? If K1 is greater than K2, then alpha 2 is less than alpha 1 because K directly proportional to tan alpha. Alpha 2 is less means, see, if the alpha 2 is less, then this flow line, this is the flow line, right? This flow line deflect towards the normal or away from the normal. Deflect towards the normal. See, this is alpha. This is going to be alpha. If alpha 2 is going to be less, then the flow line will deflect towards the normal. Flow line will get deflected towards normal. Sir, how this K directly proportional to tan alpha? If there is a proof, you don't worry about the proof. You don't require the proof. If you want a proof, you please mail me. I can attach the proof also. But I am not going to discuss any proof over here. So flow line will get deflected towards the normal. Similarly, if K1 is less than K2, then alpha 2 is more than alpha 1. Flow line gets deflected away from normal. Away from normal. That's it. Mr. Sricharan sir, as the main purpose of dam is to store water, we are providing gravel as filter media as a tool such that water can easily escape. It is not that failure of dam as water is seeping from the downstream side. See, Mr. Sricharan, here the water will enter, but it is not going to be like liters and liters. It is going to be very, very less amount. And if that less amount will stagnate in the dam, that will cause more effect than relieving the water from the dam. So though the dam purpose is going to be to store water, due to permeability of the soil mass, water will seep into the soil or not. And if you allow the water to still over here, then the soil becomes saturated and slowly it tries to erode. Sir, when alpha, see, when K1 is equal to K2, then alpha 1 is equal to alpha 2, then it is going to be isotropic soil, right? Then it's going to be isotropic soil. Okay, so that's all with this topic. In the case of anisotropic soil, so what happens when the flow gets deviated or deflected? So these are the things from this chapter. With this, we have completed this chapter. Now let's see some classroom practice questions. Now see this question. Upstream side of the soil is also erode, no sir, due to water pressure. Then there also will have to provide gravel or anything else. See, my dear anonymous attendee, there are on the upstream side, we are going to provide the block protection also, that you will be understood in irrigation. So don't worry, in irrigation, there is a topic known as hydraulic structures. There you can understand that anonymous means this upstream side also. Don't worry as of now. So even if I less than ICR, quicksand exists. See, when I less than IC, then it is going to be fail. Once the quicksand condition occurs, then it is about to fail. What is the meaning of failure? Soil will erode. That's why not seen any gate question on focal distance. So that's the reason why I told you not to give much importance for the focal distance. The topic is for the ESE. So don't worry about that focal distance and all those things. Now you see the question number 1. This is one of the previous means this type of question has been asked in one of the previous gate. I hope you have seen this type of question in chapter number 7. So now you observe clearly here. Now after all this discussion, if you don't say me what is this condition, then I won't be able to help you. You see, this is a figure, and this is a ground level or bed level. Above this is a pond. In the pond, this is the water table. And below, what is this clay? And this is going to be sand. Yes or no? And when they insert the stand pipe in the sand, water level in the stand pipe is going to be rises up to this level. Now, can you please tell me, is it under Artesian condition or not? Definitely, it is going to be under Artesian condition, because this is a sand permeable layer present below the impermeable layer. Then definitely the confining is there, confined pressure. So the difference between these water levels, this is water levels. How much difference over here? 5 meters. Now with this, see, definitely now you can observe the uplift pressure will be there or not? Yes or no? Due to this uplift pressure, now water starts to seep into the soil. Now water starts to seep into the soil. Now what they're asking is, at a site shown in the figure below, water rises to elevation 5 meters in standpipe inserted in the sand stratum. The quantity of flow into the pond from the clay layer per meter square of the pond. See, they're asking what is the quantity of the flow. See, you observe over here, due to this difference in the water levels, now the flow is going to be started through the clay. See, through this clay, how much quantity of water is going to be added to the pond? How much quantity of water? Q in terms of meter cube per day and per meter square of the pond. What is the meaning of per meter square? Per area, per meter square. So actually they are asking not a discharge, they are asking meter cube per day per meter square, which is nothing but the velocity. Which is nothing but the velocity. So here you need to understand that the flow is happening due to difference in the water levels. The flow is happening as an upward seepage or not, and how much distance it is going to be traveled in the clay layer. This is the distance. What is this distance, please? This distance is going to be 5 meters or not? The distance is going to be 5 meters, and the difference in water levels is 5 meters. And how to find out the discharge per unit area? V is equals to K into I. V is equals to K into I. I want to solve here itself. That's the reason why I don't go for the others. So now you see, as you know, V is equals to K into I, because discharge per area is equals to V is equals to K into I. So now V is equals to, what is K value here? 10 to the power of minus 5 into centimeters to meters. See, I am converting the centimeters to meter, 10 to the power of minus 2 into, they are asking per day. Per day means they are giving a second. 60 minutes into, 60 seconds into 60 minutes into 24 into I value. What is I value over here? I means H by L. H5 by 5. So please find out this answer. The answer is going to be, see, 60 into 60 into 24 is 86,400. Into 10 to the power of minus 7. So which is going to be 8.64 into 10 to the power of minus 3 meter cube per day per meter square. So this is the value. The answer is going to be 8.64 into 10 to the power of minus 3 meter cube per day per meter square. See, this much amount of discharge per unit area will enter into the pond. You observe here per day 8.64 10 power of minus 3, very less value. What is the meaning of 8.64 into 10 power of minus 3? 0.00864 meter cube, or I can write 8.64 liters, because you know that 1 meter cube is nothing but 10 to the power of 3 liters. So if I write this meter cube as a liters, then 1 meter cube is equals to 10 to the power of 3 liters. Then the discharge per unit area is going to be 8.64 liters per day. Array for 1 day, throughout the day, you're going to get 8.64 liters. Now, just I'll tell you. In your home, you please keep a bucket under a tap, and you just release the tap so that only one drop is going to be fall at a time. A small droplet is going to be formed, and you keep that for 24 hours. After 24 hours, you go and measure how much volume of water you are going to get. Then definitely that is going to be more. Yes or no? Because every second a small drop is going to be fall. Definitely 24 hours, it can see normally our bucket volume sizes are 25 liters. Whatever the bucket we use in our home, so normally it is 25 liters. So by the end of the day, I hope most or 50 to 70% of the bucket will fill, which means 15 to 20 liters, means 12 to 15 liters. But here 8.64 liter, very less amount of water will flow here. Sir, why you did not take the length from the sand, sir? See, sir, they're asking which layer, sir. You see, observe, from the clay layer, which means this is the clay layer, right? The flow is going to be passing through the clay layer. So I have to take the clay layer length, not the sand layer length. So forget about the sand layer. So the answer is going to be 8.64 into 10 to the power of minus 3 meter cube per second. Sir, here, what is the value of artesian head, sir? You please tell me, sir. See, as they did not mention the exact position they have kept, the total artesian head. See, if they would have given the exact position, then you can find out the artesian head. So if I would have mentioned you, this value is going to be somewhere 3 meters like this, then I can say the artesian head. But here, I don't require any artesian head, because I'm not discussing about failure, I'm discussing about the seepage. Okay, so that's about yes. Now, let's see this next question. Somebody, sir, please explain the question number for question number. I'll tell you, Re Baba, I'll tell you. Wait for that. Keep some patience with you. Keep some patience with you. I am not playing any dumb slots over here. Sir, in GATE, it is necessary to mention unit in answer. Sir, it is not necessary to mention unit in answer, but they will give the units. You have to convert your answer into that units. Sir, how the velocity we calculated in per meter square, please explain. Arey Baba, they have given, they are asking meter cube per day per meter square, discharge per unit area. Okay, fine. Now, let's see the next question. Question number 2. You see the question number 2. In the case of the question number 2, look, I have given you the vertical directions of permeability and horizontal direction permeability. The coefficient of permeability in horizontal and vertical direction, Kx and Ky is given. The base length of concrete dam resting in the soil is 100 meters. When the flow net is developed for the soil with 1:25 scale in a vertical direction, the reduced base length of the dam. See, I told you earlier in yesterday's class, sir, he is asking discharge, sir. Arey Baba, आपको दिमाग है तो इधर रखो रे भाई. Why you people come right? What is this? What is this? Meter cube per day per meter square. What is the meaning of per meter square? Per meter square means area is equals to 1 or not? Yes or no? What is the meaning of meter cube per day per meter square, which is nothing but meter per day only, right? Okay, fine. So now, coming to the question number 2. You see this question number 2. See this question number 2. They have given Kx and they have given Ky, which means the soil is an anisotropic soil. For the anisotropic soil, are we going to apply the flow net directly? No. I told you clearly, if you want to apply the flow net to the anisotropic soil, first of all, you have to transform it. How we are going to transform? We reduce the base length from capital B to small b. So now, let's see this question. So, classroom practice question. Question number 2. If you see, given Kx is 3.46 meter per day, is it? Yes. And 1.5 meter per day. .4 meter per day. Kx is 3.46 meter per day and Ky is 1.4 meter per day. Given the soil means the base length of the dam, original width is going to be 100. Original width is 100. So you know that flow net is constructed by reducing the base length. By reducing the base length to b. So now you tell me, what is this b? B is equals to root of Ky by Kx into capital B. B is equals to root of Ky 1.4 by 3.46 into what is B? 100. So now the small b is equals to 1.4 by 3.46 root of answer into 100, which is going to be 63.61 meters. 63.61 meters. Okay. This is 1.5, right? Sorry. This is 1.5. Yes. So now 1.5 by 3.46 root of answer into 100, which is going to be 65.84. Okay, I understood. 65.84 meters. See, this is the reducer. But while we are drawing the flow net, we have to take the scale factor, right? So once Uh, after transformation from anisotropic to isotropic, same scale can be used in both vertical and horizontal directions. So now you go back, once you observe, whatever the scale I provided over here is a 1:25 scale factor in the vertical direction. So 1:25 given scale 1:25. Sir, what is the meaning of 1:25, sir? Sir, one part of the model is equals to 25 parts of the prototype, sir. One part of the model is equals to 25 parts of the prototype. So whatever the prototype means actual. What is the meaning of 65 meters? 65 meters means it's a long width, which means that is in a reality, means prototype, actual structure. So now what I want is I have to draw into a graph. So when I want to draw into the graph after given scale, the given scale is going to be 1:25. So the reduced base length is equals to 65.84 into 1/25. See, you are reducing the scale by 25 times. What is the meaning of a scale? You are reducing the scale by 25 times. This is the actual one, 65.84. Now you reduce it to 25 times. Now what is the answer? 2.63 meters. I have asked you to solve this question yesterday. So now this is the solution. The people who have done this one, that's fine. The people who have not done, you please check over this one. Mr. Jagdish Marpu, sir, if base length decreases, is the strength of the dam decreases? Arey Baba, we are not reducing the base length. For finding the flow net, we reduce the base length. See, we construct the dam with 100 meters only. But while you are going to analyze, you don't take the 100 meters. You take it as 65.84 meters. Then only you convert the anisotropic nature into isotropic nature. Okay, fine. So now, let's see the next question. You see this question number 3. I'll be solving this question here itself. This is the previous IS question. Sir, what if horizontal scale is given, sir? Sir, आपको थोड़ा दिमाग है sir? दिमाग है तो इधर रखो sir. ये क्या है sir? Same scale can be used in both vertical and horizontal directions, sir. कोई भी, whatever the scale they have given, whether it's a vertical scale or horizontal scale, you have to use it both. Means the both scales are same. The meaning of isotropic, what is the meaning of isotropic? In vertical and horizontal, everything is going to be same, right? Okay, now you see everybody here. This is a question number 3. In this question number 3, in the schematic flow net shown, see this is an earth dam, right? And you see this is nothing but the graded filter I have provided you. This is nothing but a gravel, Nana. So now they are asking the hydraulic potential at A. What is meant by hydraulic potential, sir? Seepage head yet A. Seepage head yet A. So now you observe over here clearly. If you see, this is A, right? Yes. So how to find out seepage head at A? Seepage head at A is nothing but total hydraulic head minus head loss up to A. This is n number of times that I have been discussed. Now you tell me, What is the total hydraulic head over here? The total hydraulic head here is 18 meters. The total hydraulic head is here as 18 meters. Now, what is the number of drops over here? Please represent the number of drops, Nana, everybody. What is the number of drops? 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 drops are there. Total, I hope if you observe, there are total 9 drops. So if you don't observe, I'll write it again. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So total 9 drops were there. So 9 ND is equals to 9. Then what is the single drop? Single drop is equals to total H by ND, which means 18 by 9. So each drop is going to be 2 meters. Now up to A, how many number of drops are there? 1, 2, 3. 3 drops are there. So head loss up to A is equals to N into delta H, which means 2 into 3 into 2, which is going to be 6 meters. Then seepage head at A is equals to 18 minus 6. The answer is going to be 12 meters of water. 12 meters of water. So see, what I have done is, this is the seepage head at A. And in order to find out the seepage head at A, you see, this is a seepage head at A, right? In order to find out the seepage head at A, you need to find out the head loss at A. How to find out head loss at A? You need to find out the single drop. So the single drop is going to be 2 meters, which means for 1 drop, you lost 2 meters. And up to A, how many drops are there? 3 drops are there. So how much you lost? 6 meters. I don't need to go all these things also. Now apply the logic. Think carefully. Think carefully. What is the total hydraulic head here? 18. And what is the total number of drops here? 9. Think carefully. Array, total drops 9 and total hydraulic head is 18. So for 9 drops, the hydraulic head is 18. Now, by the time you reach A, how many drops you lost? 3 drops you lost or not? Which means 1, 2, 3. 3 drops you lost. Then how many drops you have? 6. For 9 drops, 18. For 1 drop, how much? 18 by 9, 2. Yes or no? And by the time you reach A, how many drops you lost? 3 drops. Are each drop 2 meters? 3 drops. 3 into 2, 6. With what you started? 18. But how much you lost? 6. Then what else remaining? 18 minus 6, which is going to be 12 meters. So that's all over here. Yeah. So this is the question number 3. Now coming to the question number 4. Now most of the people they can find out this, but you see, sir, Mr. Gautaman, how you fix that 1 drop for 2 meters, sir? Sir, I did not fix the 1 drop as 2 meters, sir. You please go through this one once again. I'm just telling you the logic over here. The logic is, what is the total head drop over here? 18 meters. And how many number of drops? 1, 2, 3, 4, 5, 6, 7, 8, 9. So total number of drops are going to be 9. Then each drop, single drop is equals to H by ND, 18 by 9, which is going to be 2 meters. So when you travel 1 drop, you lost 2 meters. By the time you reach A, how many drops are there? 3 drops are there. So at A, Head loss at A is equals to N into delta H. So 3 into 2, which is going to be 6. So you started with 18, but by the time you come over here, you lost 6. Then at this point, 18 minus 6, which is going to be 12 meters. If you still don't understand this one, then I cannot, then I cannot make you to understand the concept. So I hope I have been explained the question number. See, I am not going to solve the question number 4 because I have explained yesterday also. But I'll show you. Means I hope everybody have done this question number 4. So now you see, most of the people may get a doubt, but I'll solve this one. So I have to listen. A masonry dam of 15 meters long. See, now they have given the length of the dam. A masonry dam. See, this is a dam. And they have given the length of the dam. What is the length of the dam here? 50 meters. So far, we consider the cube means a discharge as meter cube per second per meter length of dam or not. So now they have given the length of the dam also. Is overlying on impermeable soil, is founded on soil with anisotropic in permeability. They have given anisotropic. The upstream water level is 9.6, tile water level is 0.6. So upstream water level 9.6. Tile water level is 0.6, which is going to be difference of 9 meters. Now the question is, the vertical permeability is 1.39 meter per day and horizontal permeability is 6 times as that of vertical permeability. So vertical permeability is going to be 1.39 and horizontal is 6 times. The flow net drawn on a transformer section. Everybody please now, what is the meaning of this one? What is the meaning of this one? You see, what is the type of soil we took? Anisotropic soil. Can you apply the flow net directly to the anisotropic? No. You have to transform the section, and they have already done. They have already done the transformation. So they done the transformer section and they have drawn the flow net on the transformer section and deal the number of flow channels NF as 5, drops ND as 8. The total seepage expected per day. Now it is not for meter length. It is going to be expected per day. So I hope you people can solve, but now it won't take more than a minute. So for solving us. So now let's see this question also. Question number 4. Given K Y is 1.39 meter per day. Kx is 6 times of Ky, yes, and H is equals to head water level 9.6 minus tail water level 0.69 meters. The length of dam given as 50 meters, number of flow channels as 5, and number of drops as 8. So I hope this is the data they have mentioned. So now, yes. So they're asking expected of meter cube per day. Now, first we find out Q is equals to K into H into NF by ND, where K is nothing but Ke for anisotropic nature. So what is Ke? Root of Kx into Ky, root of Kx, which means 6 times of Ky into Ky, which means Ke is equals to 1.39 into root 6. So 1.39 into root 6. Which is going to be 3.4 meter per day. So now you please solve this one. The Q is equals to 3.4 into H value as 9 into 5 by 8. By 8, which is going to be 19.15 meter cube per day per meter. This is per 1 meter. Yes. Now total seepage is discharged into length of dam. So 19.15 into what is the length of dam? 50, which means 950 957.6 meter cube per day. So this is the value. That's a total seepage they're asking. This is per meter, but they have given the length of the dam. So now that's about the question. Now you see this question now, question number 5. This is very, very important, and it does not have a single means. It seems like a big question, but I'm telling you, there is nothing in this question. There is nothing in this question. So first, let me draw this one. Figure shows whatever the figure shows. They're saying the kx, ky, kz, which means the soil is isotropic because they have given every direction the permeability is same. So now they have given this one. So what may mentioned is how height above the ground surface the water will rise if piezometers are placed at point A, B, C, D. So if the piezometers are placed at A, B, C, and D, how high the water level will rise above the ground surface? They are not asking exact at ground surface, they are asking above the ground surface. And the rate of seepage through flow channel. Also, first, let me draw the figure. See, this is the ground level. And there is a stratum. This is a sheet pile wall. Okay. And you see the water levels I have mentioned you. This is upstream water level. And here this is the downstream water level. So now I have given you this upstream water level and downstream water level. This is a ground level, and whatever this is nothing but 4.5 meters. So and now apart from this, whatever the data they have mentioned is this is 1.1 meter. So here this value is going to be 1.1 meter. Now let's see, they have mentioned some of the see this dotted line they mentioned this as a flow line. You know that flow line, right? This is one flow line. Likewise, they mentioned two flow lines like this. See, whatever this is nothing but the flow line. Yes. Then how many number of flow channels are there here? You please tell me how many number of flow channels are there? Think and say. See, this is a flow space where the flow takes place here also. So this is a 1 and here 2 and here 3. They mentioned all these three things also. So NF is given as 3. Similarly, for ND, These are going to be the equipotential lines. They mention these as the equipotential lines. Now, how many number of drops are there? 1, 2, 3, 4, 5, 6. So what is ND over here? 6. So number of flow channels are 3 and ND is equals to 6. I hope this is the given details they mentioned. So if you see this figure also, they mentioned already clearly. So now, yes, see here 1, 2 and 1, 2, 3, 4, 5, 6. There are 6 drops are there. There are 6 drops. 1, 2, 3, 4, 5. This is going to be 6, right? Last one. So they're asking at these points A, B, C, and D. Now I'm asking you. This is a point A. Here point B, and somewhere over here point C, and somewhere over here point D. You observe here clearly. Now, while I was explaining you yesterday, now I'll show you that also. While I was explaining you, see, yesterday I explained you the characteristics of flow net Arna. So while I was explaining you the characteristics of the flow net, you please observe over here. These are nothing but the equipotential lines Arna. Now, from one equipotential line to other equipotential line, there is a head loss. What is that head loss? Delta H. So if I insert a piezometer, then the water level in the piezometer will fall by delta H or not? Yes or no? Now, by the time you reach go for the second drop, then how many drops are there? 2 drops. From here to here, there are how many drops? 2 drops. So now, between any 2 equipotential lines, there is a 1 drop. And that drop is nothing but fall of water level or not? Yes. Now, by using the same concept, I'm going to be explain this. So now you see here, I will insert a piezometer over here. So they're asking is above ground level. Above ground level. If you observe, if I would have inserted a piezometer, at this point, see, this is at ground level or not? This is at ground level. Water level will definitely rises to this height because that is at ground level, right? But they are asking above ground level at A. So now you tell me, if I would have inserted a piezometer over here, come on. If I would have inserted a piezometer over here, so you please tell me, see how many number of drops are there over here? 1 drop. See, by the time you reach from this point to this point, how many drops are there? 1 drop. So when you are going to lose 1 drop, then the water level in the piezometer rises to certain height, and this is going to be delta H. This is going to be delta H. Yes or no? Now if I insert one more piezometer over here, now if I would have inserted one more piezometer over here, so now you see, this is 1 and this is number 2 drops. So now in this piezometer, water level will rises to certain height. Again, 1 more drop would be there or not? So this is delta H and this is also going to be delta H. So from the water level, how many number of drops are there? 2 drops. Yes or no? So now above the ground level, you see, above the ground level at A, the pressure head HP is equals to, can I say, above the ground level, the number of drops are going to be, pressure head is equals to, what is the total water level above the ground level? 4.5 meters. minus, can I say n into delta H? Yes or no? N into delta H. So at A, n is equals to 1. Because how many number of drops are there? One drop only. At A, how many number of drops are there? One drop only. One drop means one head loss. So now how to find out this head loss, sir? You need to find out this head loss first of all, right? So what is the difference between these water levels? H is equals to 4.5 minus 1.1, which is equals to 3.4 meters. So how many number of drops are there? 6 drops are there. Then what is each drop? Each drop is equals to H by ND. Then delta H is equals to 3.4 by 6, which is equals to 0.567 meters. So the meaning of this one is in simple words. See, I will erase this one. So the meaning of this one is by the time you go for B, how many number of drops you are going to lose? 2. By the time you reach A, how many number of drops you lose? 1. Total height is 4.5 and water level falls by 1 drop. So 4.5 minus 1 into 0.567. What is this answer? Which is going to be 3.933 meters. Similarly, at B, what is the pressure head? At B, 4.5 minus 2 into delta H. Because by the time it reaches B, how many number of drops are there? What is the meaning of N? N means number of drops up to section A and B. So now you see here n is equals to 2, 4.5 minus 2 into 0.567. So this water level, this is the water level falling of water level or not? How many drops? 2 into delta H. Then 4.5 minus 2 into 0.567, which is going to be 3.36 meters or 3.367 meters. Now you see up to C and D, how many number of drops are there? 5. Because as C and D are going to be lies on the same plane, as C and D lies on same equipotential line. Same equipotential line. So now by the time you reach C, how many number of drops are there here? 5. By the time you reach D, how many number of drops are there here? 5. So which means if I insert a piezometer, the water level above the piezometer means above the ground level would be same. Yet C and D. See, please don't think this height. They are asking above the ground level, because you please see this point above the ground level. So now above the ground level, how many number of drops are there up to C? Number of drops are there going to be 5. Then what is the pressure head over here? 4.5 minus 5 into 0.567. What is this value? 0.567. 4.5 minus, which is going to be 1.67 meters. A and C also lies on same equipotential. How it is going to be? See, this is a, what is this value? What is this? This is a sheet pile wall. It is a differentiating A and C. So don't think A and C are both at the same time. Look, see, here I am discussing, Mr. Harish, to find out HS of X. Sorry, Baba, HS means C phase head, Mr. Harish. HP means pressure head. Pressure head is different. C phase head is different. First, find out the difference between the, means get down the difference between C phase head and pressure head. Both are not same. C phase head is different. Pressure head is different. Okay, I am asking you pressure head, not the C phase head. So this is the question, and I hope you understood this. And there is one more question in this. That one more question is, yes. So not only that one, but also the rate of seepage through flow channel 2 per unit length. See, they're asking the rate of seepage means discharge. And channel 2, which is going to be delta Q2, they're asking channel 2. You know that how many number of flow channels are there? 3. You know that total discharge is nothing but delta Q1 plus delta Q2 plus delta Q3. And you know that every flow channel has the same discharge. So I can write delta Q2, they're asking, is equals to delta Q only, because every flow channel is going to be same. So now can I write delta Q is equals to Q by NF? And what is Q? K into H into NF by ND into 1 by NF. K into H into N by ND. So now NF and NF gets cancelled down. In other words, you please observe, you know that Q is equals to K into H into NF by ND. See, they are not asking total flow rate. They are asking only through channel 2. Through channel 2. So now Q is equals to K into H into NF by ND. Now can I write Q by NF is equals to K into H by ND? Yes. And what is H by ND over here, please? H by ND means K into delta H. K into delta H. So what is the K value they mentioned in the question? The K value is 4 into 10 to the power of minus 3 centimeters per second. And they are asking this value in terms of meter cube per second. So now what you need to do is the given 4 into 10 to the power of minus 3 centimeters per second, given K is going to be 4 into 10 to the power of minus 3 centimeters per second. So now I am going to convert that form 4 into 10 to the power of minus 3 centimeters into 10 to the power of minus 2 meters. See, this is the conversion into what is delta H? 0.567. Which is going to be 2.268 into 10 to the power of minus 5 meter cube per second per meter. So this is the thing that you need to get down in the case of the discharge. As they're asking the flow passing through channel 2. They're asking flow passing through channel 2 only. They are not asking the total flow rate. They're asking flow passing through channel 2. Mr. Amit, sir, whatever heads we have calculated are seepage only, na, sir, because they are total head minus head loss. Remember, this is seepage head. Okay, this is seepage head. Total hydraulic head is a 3.4 meters. I am asking, see, this is nothing but pressure head, Baba. Please, piezometer means pressure head. Get down the difference. The difference between water levels is a hydraulic head, and this is a piezometric head. See, total head is equals to pressure head plus datum head. So pressure head is equals to total head minus head loss. Yes, sir, if they ask seepage head, na, you please tell me, if they ask seepage head at A, then that is going to be, see, what is the seepage head? You starting with 3.4. And if at A, one drop is going to be happen, 3.4 minus 1 into delta H, then that is going to be seepage head. But I am asking you the pressure head. Pressure head is different. Seepage head is different. You see, in the same question, if I ask you what is a seepage head over here, you please observe. If I ask you What is the seepage head at find seepage head at A, B, C, D. Now, seepage head at A is equals to total seepage head minus head loss up to A, H minus N into delta H. So, see, what is H value over here? 3.4 minus 1 into 0.567. What is this value? 3.4 minus 0.567. 2.833 meters. Now you tell me, you please look over the pressure head. See above the ground level, see the pressure head is a total, Nana. The pressure head is going to be total. And do you know this length? Do you know this length? No. That is the reason why in the question they mentioned clearly, Baba, you insert a piezometer at A. In the piezometer at A, what is the water level that rises above the ground level? Because they did not mention the length below the ground level. So I am finding everything above the ground level. I hope now you people have understood what is the difference between the pressure head and the seepage head. Seepage head is this one. Seepage head is 3.4 meters. You started with 3.4 meters. Seepage head is different and the pressure head is different. Pressure head is this water level in the piezometer minus head loss. So similarly, seepage head at B is equals to head minus 2 into delta H, which means 3.4 minus 2 into 0.567. This is going to be 2.267 meters. That's all. What should be done if they ask for 2 channels? Multiply into 2. Please explain point C and D. Point C and D. C and D are lying on the same equipotential, right? See how many number of drops over here? 1, 2, 3, 4, 5. Yet D, how many number of drops are there? 5. Yet C, how many number of drops are there? 5. So yet C and D, the number of drops are going to be same. Now you tell me, is it a difficult topic? These things we discussed in the case. Just it's all about application, Anna. Think about the application. If you understand that, then you can get down any answers. Yes, will seepage head be same at C and D? Yes, sir. At C and D, seepage head is going to be same. Miss Nikita, what if they ask for channel 1? I told you, Nana, every discharge is same. What is the, I'll write this point also. Okay, fine. Delta Q is equals to delta Q1 is equals to delta Q2 is equals to so on. Every flow channel has the same flow rate. So somebody may ask, sir, what is the flow rate in the channel number 3? That is also going to be same. Each and every flow channel has the same flow rate. In channel 2, 2.268, channel 3, 2.268, everything is going to be same. So it is A and C. Yes. So that's all with this chapter. And I am not going to discuss this question number. Question number 6, I hope you people can do it one. They have given already everything. In the question number 6, they give the length of the exit field as 1.65 meters. They have given this one. And they give you know the difference between these water levels. What is this difference between water levels? 4.2. And how many number of drops are there? 1, 2, 3, 4, 5, 6, 7. Total 8 drops are there. So ND is equals to 8. you please find out delta H as 4.2 by 8. You will be get down that value, and you find out the I exit. I exit is equals to delta H by delta L at exit. They're asking about the factor of safety, IC by I exit. So I hope most of the people have done this question. If not, you please go through this one, because I have explained the similar type of question as a gate question yesterday also. This is just similar to the previous gate question. If we have solved this one, fine. Else, it's up to you. Mr. Anonymous Identity, how many times you will ask the same question, sir? If I less than IC, quicksand exists or not? Arey Baba, I is equals to IC means quicksand. If I less than IC, then definitely the quicksand is there and failure is going to be there. This is the yesterday you asked this, yesterday I cleared. Today you asked this, today also I cleared morning. And now also you are asking. See, the answer is going to be 3.4. You can get done. If you have done this one, that's very good. That's you people have understood the topic. The answer is going to be 3.4. So with this, I have covered each and every topic in this chapter. Now we did chapter number 6, chapter number 7, chapter number 8, and chapter number 9. So that's all about the CPS chapters. And now, sir, in offline lectures, you don't get angry. See, in offline lectures, generally now also I'm not getting angry. It's not anger. It's about the irritation, because I discuss the same things, and even if I discuss the same things and I'm providing you the written notes of my hand written notes PDF, which means I'm writing each and every point on that, and I'm giving you the recorded lectures, and I'm asking you, do you think in offline lectures are you getting any recorded classes? Are you going to get any recorded classes? No. And you have to write the notes on your own, which means you might do some mistakes while writing. And here, whatever I'm speaking from my mouth, I am writing most of those points in the notes. I'm providing you the notes, and I'm providing you the recorded lectures wherever you go, wherever you see, whatever the time you can hear that. And I am repeating the same number of questions and repeating the same concept n number of times, providing you previous gate, previous IES, and some classroom practice questions. I'm providing you these many sources, and I'm telling you, compared to offline, I'm giving you more than 200% in the online. And even if I am giving these many things, if you're asking the same doubts again and again, which means either it's you're not listening to the classes, or you're not reading in the home. So that's the only two reasons. Or the third reason is that I'm not able to make you understand, or I am not fit for making you understand. So you please take whatever the option for you. Yes, so with this, now we'll have a small break. It's 11:04. I'll give you break up to 11:25. So we'll start our next session at 11:25, and we're going to start the chapter number 10. Today we are going to discuss about the chapter number 10. So with this, the CPS chapters has been completed. So now we'll be discussing about the chapter number 10. So please have a break, and after the break, we'll see the next session. So now it's about 11:04. So please come by 11:25. Okay, now okay, I hope everybody have been here. Yes. So now we are going to discuss a new chapter. So that a new chapter is chapter number 10, stress due to vertical external loads or vertical stress distribution. Stress due to vertical external loads or stress due to vertical external loads or stress due to or vertical stress distribution. See, in chapter number 7, I have explained you. In chapter number 7, just in chapter number 7, we discussed about stress due to self weight of soil. If you remember, there I did not discuss any external load. Means external load means whatever the structure load is external load or not. So there I did not discuss any stress due to external load except for surcharge. But now here we are going to discuss about the stresses due to vertical external loads. So in the case of the self weight of the soil mass, we discussed about total stress, pore water pressure and effective stress, because in soil there are solids and there are water. So water pressure is nothing but pore water pressure and soil solids pressure is nothing but effective stress. But now due to external load, how these stresses are going to be developed in a soil mass and how those stresses are going to be distributed along the depth. I'll give you a quick summary, quick revision of 6, 7, 8, 9 at the end of the class. At the end of the class, I'll give you. Okay, so I have all the PDF. So I'll give you all the quick summary at the end of this session. Means after 1 o'clock. So I'll be taking today 1 hour of doubt session. So up to 2 o'clock, I'll be taking a doubt clearing session from 1 to 2. And meanwhile, in that, I'll give you 15 to 15 minutes of summary of chapter number 6, 7, 8, 9. Then I'll be taking questions from you also. So don't worry about that. Now, what are the theories that we are going to discuss in this case is theories are number 1, Bosnisk's theory. Second one, Westergaard's theory. Newmark's chart. Newmark's method. Newmark's method and approximate method. So this is also known as a 2 vertical to 1 horizontal distribution method. So these are the some of the methods that we are going to see, and we'll see what are the silent features of each theory and for what type of loads they are going to be discussed and how to find out the stresses at any depth. So first of all, let's go with the Bosnisk theory. First one, Bosnisk theory. So for every theory, there must be some assumptions. And what are the assumptions in the Bosnian theory is soil is elastic. What is the meaning of soil is elastic? Elastic means stress directly proportional to strain. Yes or no? So if you apply the load, soil will undergoes compression. If you remove the load, then it tries to regain. So soil is assumed as a elastic member, and soil is homogeneous, isotropic, and semi-infinite. Semi-infinite. Soil is homogeneous, isotropic, and semi-infinite. See, I already explained you what is meant by homogeneous. If you take a soil mass, in that soil, if you go for at any point in a particular direction, properties are going to be same. So here sigma and here also sigma, stress is going to be same. Then we call it as homogeneous. And for the isotropic, I mentioned you take a particular point in any direction. If the stress is going to be same, then we call it as isotropic. And now coming to the semi-infinite, this is the one of the best means important assumption in this series. The assumption is we assume the ground level as horizontal, right? So now you see this is a ground level. You observe beneath the ground level or above the ground level. So for suppose you are standing here. Can you see what is the length of the soil mass in this direction? You are standing over here. Can you tell me what is the length of the soil mass? No. You can tell me the length up to which you can see, but is it the end of the soil? No. Can you see what is the length of the soil mass in this direction? No. Can you tell me what is the depth of the soil mass in this direction? No. Can you tell me any other direction? No. So now, wherever I stand, in all the directions, see, I am standing over here in all the directions, whether I see front or side or back or below, the soil mass length is infinite. Then what is the meaning of semi, sir? Sir, you see above, sir. When you see above, is there any soil mass, sir? No. So here the meaning is, this is a ground level. On the ground level and beneath the ground level, soil is infinite. And above the ground level, there is no soil. So semi means half. And below the ground level, everywhere it is going to be infinite in nature. So we call it as a semi-infinite. And these are the assumptions. Apart from this, the most important assumption is the load should be taken as point load. See, the Bosnian theory has taken for point load theory. So point load should be concentrated point load at ground level or ground surface. So these are the assumptions made by the Bosnian theory, and these assumptions are very, very important in the case of the IES prelims. See, for the people who are preparing for the IES, mind it, every chapter has some theories and every theory has some assumptions. Those assumptions are very, very important. They can ask you a question as, which of the following assumptions regarding to Bosnian theory is not correct? They'll give the statements and they'll ask you out of those statements which are not going to be correct. So now here Bosnian theory. So in the case of this Bosnian theory, how it is going to be explained. Have a look now. If I say this is a ground level, see, this is a ground level, and whatever we are going to discuss is a concentrated point load. What is the meaning of concentrated point load? The meaning of concentrated point load is a point load acting at the center, So now so we can tell the depth of the soil. See, you can tell the depth of particular soil, but what is the total depth up to the core? There is a soil mass up to the rock, or right? So in all the directions, wherever you stand, in all the radial directions, this is the one direction, this is the other direction, this is the other direction. The depth is means the length of the soil is infinite. These theories are required for gate. Yes, they will required for the gate. So in the case of the one more assumption, C is going to be homogeneous and isotropic, right? Then it's going to be uniform. Now the soil mass, the ground level means this is the ground level. As we are discussing about, the whom point load, concentrated point load. So now let's say this is a concentrated point load of intensity Q. So the point load means its units are going to be kilonewtons. See, the Kn is not something. The units of this load is going to be kilonewtons. There is a point load. Now my question is, now you are there. Just imagine. Okay. Just imagine if this is the ground level. Observe carefully. I hope you can see now. Now I'm maximizing the video. So now you see this is a ground level. If this is the point load acting. Now, if I apply this point load, due to this load, definitely some stress will be developed in the soil mass or not? Yes. Now, what happens if you apply this load? Due to that, how does this stress is going to be developed? Below the depth, below the ground level. See, just imagine if you punch your foot on the ground. If you punch your foot on the ground with some power, it will create some stress in the soil mass. My question is, as the depth of the soil increases, does the stress created by you will increase or decrease? It will decrease. Sir, due to self weight, it is going to be increased, sir. Sir, as you go deeper and deeper, self weight of soil increases, sir. So stress increases, sir. But in the case of external load, where you are applying the external load? At the ground level. At the ground level. And at that ground level, stress is more. As you go deeper and deeper and deeper, the stress due to external load will decreases. The stress due to external load will decrease as you go deeper and deeper. Similarly, now one more example. Look, when I punch my foot over here, the person who stands next to you will feel the impact. Definitely. Yes or no? And the person who is 110 kilometers away from you, and the person who is 500 meters away from you, does they feel any impact of your load? No. Which means wherever you are going to impact, the person who is next to you will feel that impact. But the person who is very far away from you, he does not feel any impact. Which means if you are a person standing over here, in all your radial directions, as the distance increases in all the directions, the stress due to this load will decrease. So I can say, if you apply an external load over here, in all the directions, this is the perpendicular to the board, in all the directions, as a distance is going to be increases, the stress due to this load decreases. And in the depth direction, as the depth increases, the stress due to this load is going to be decreases. So how, sir? I'll show you with the equation. Now, I'm going to plot an isometric projection over here. So you please have a look over that. See, this is a perpendicular to the board, Nana. Now, okay. So now if you observe, this is the place where I have applied the load. Let's take this direction as x, and in this direction the distance is y. Now what would be the stress? What would be the stress? You see, observe over here. What would be the stress due to this load? See, this is a top view. I am showing you the top view. You are standing over here. You are standing over here. You are standing over here. This is a load in the x direction and y direction. So I want to find out the stress due to this load at this point. So at this point means definitely from here to here, there must be some distance r naught. And what is this distance is nothing but radial distance r, where r is going to be radial distance. So how to find out the radial distance here, please? I want to find out over here, and that too, you see now, this is going to be the depth direction r naught. Now, you see, this is the depth direction. Let's say this is going to be Z. So now I want to find out the stress. I want to find out the stress. So below the So now you see, I want to find out the stress below this point and whose depth is going to be at a depth of Z. So you know that here, what is this distance? This is going to be radial distance R. So I am representing R. See, this is R, where R is going to be radial distance or okay, fine. I hope you people represent the R in different fashion. So this is R. This is not gamma nana. Don't think, please, that is not gamma. That is R. R is a radial distance. Now, I want to find out what is the vertical stress at this point. So now you tell me, this is a load I have applied, and on the horizontal direction X and y direction Y. And if this is the point where I want to find out, so what is the vertical stress at a depth of Z? So this is the condition. I hope you understood the meaning. Ground level, apply the load at some corner beneath that. So now what is the radial distance for here, where R is radial distance from point load to point of consideration. From the point load to point of consideration. This is our point of consideration and at a depth of what? Z. So now from figure R is equals to, can I write root of x square plus y square? Yes. For the figure R is equals to root of x square plus y square. Now where sigma Z is equals to vertical stress at any depth Z. See, here there is no effective stress, there is no pore water pressure, because we are discussing only external load, no water. So whatever the stress here, total stress and effective stress both are same, because there is no pore water pressure. So I am not going to define any effective stress, and J, I'll say just simply sigma. Sigma means total stress due to external load. So the stress due to vertical external load is known as a sigma Z at any depth. Now for this, this Bosnick has provided a solution. That solution is sigma Z is equals to 3 by 2 pi into q by Z square into 1 by 1 plus r by Z whole square whole to the power of 5 by 2. Whole to the power of 5 by 2, r by Z whole square whole to the power of 5 by 2. See, in this chapter, I am telling you in the starting itself, in this chapter, you don't need to worry about the derivations. Don't look over the derivations. Wherever the derivation is required, I said you. And here also, if there is any, if there is any requirement of the derivation, I will tell you. But there is no requirement of the derivation. Instead of wasting our time for these derivations, so let's focus what are the terms in this equation and what is the importance of this equation. This is not an empirical formula. This is from the means he has done some mathematical analysis. There is a derivation. That's what I am saying. When there is a derivation, the derivation means there is some assumptions are there. Based upon assumptions, he has done some numerical analysis and mathematical analysis. So don't worry about the derivation. Now, you see, so in this equation, if you observe this sigma z, please, this sigma z is a function of C. Once I apply the load Q, that is going to be constant. For a given load Q, the sigma z is a function of whom? Z and R. So from this, for a given Q, see, don't think this is going to be a discharge. This is a point load. Don't think Q is a discharge. This is a point load. So now, for a given Q, sigma z is a function of R comma Z. Sigma Z is a function of R comma Z, which means if the radial distance changes, effective means this stress is going to be changes. If the depth changes, the stress is also going to be changes. Sir. What's it confusing, Ray? This is a see, whatever this is nothing but this is the equation done by the Bosniak. What is there to confuse? See, this is the load, and due to this point load, I want the stress at this point and that too at a depth of Z. So this point you observe, whatever this point I'm showing you, this point is at a radial distance of R and at a depth of Z. You please try to analyze yourself. For example, in a room, this is your room. Let's take your room. This is a four corners of the room. You are standing on one corner. And if you apply a load over here, what is the stress at the other corner? And that too at a depth of Z below that corner, means below that slab, what is the stress at some depth of sigma Z. So this is entire, this entire is going to be the soil mass over here. Now, where sigma Z is a function of R comma Z, where R means radial distance and Z means the vertical depth. Now, you see, for a given Q, as I told you, the sigma Z is going to be a function of R comma Z. So now, just wait for a moment. See, if I ask you, if sigma Z, I want below the point of application, below the point load, just below the point load, you see, now, if I ask you to find out the vertical stress at this point, now if I ask you vertical stress at this point, can you please tell me what is the radial distance? Are Baba, you apply the load over here, and below that load itself, I am asking you the R stress. What is the radial distance now? 0. What is meant by radial distance? Distance from point load to point of consideration. When the point load and the point of consideration both are same, so below the point load, R is equals to 0. At any depth below the point load, R is equals to 0. When R is equals to 0, then what is the sigma Z, please, coming to the same equation? Now you please look over here. When r is equals to 0, then 0 by anything is going to be 0. 1 plus 0, 1. So if you see this equation in the same equation, let me write down. See, as of now, it may be difficult to understand, means to remember, but by the end of this session, I'll make sure you will understand this one clearly. So don't worry about that. Whole to the power of 5 by 2. So now, if I keep r as 0, then 1 plus 0, 1. 1 by 1, 1. 1 to the power of anything, 1. So then sigma z is equals to 3 by 2 pi into q by z square. And this sigma z 3 by 2 pi can be written as 0.4778 into q by z square. See this 3 by 2 pi value. What is 3 by 2 pi value? Please calculate. So if it is going to be 3 by 2 pi, I can say it's going to be 0.477. So you can end up with the 477 itself if you want, into q by z square. So this is the equation. So first of all, whatever the total vertical stress at a depth z I am considering here, and now I am going to give you at any depth below the point load r is equals to 0, and there is one more equation. The other equation is radial shear stress, represented with tau rz. You go over here. See, this is an element, right? On this element, don't you think there is a radial shear stress? Because you take any body, and I'm just showing you over here. You take any soil element. If this is a soil, see, this is a vertical stress sigma z, then definitely there must be some radial shear stress, then this is going to be tau r z. So if this is going to be the vertical stress sigma z, then what is the radial shear stress? See, normal stress means, vertical stress means perpendicular to the plane, and along the plane, what is the stress? Shear stress. Perpendicular to the plane, normal stress. Along the plane, shear stress. So the radial shear stress is going to be at any depth over here, whatever the radial shear stress is going to be, tau rz is equals to sigma z into r by z. Sigma z into r by z. So now you see here, below point load, r is equals to 0. When r is equals to 0, then the radial shear stress is also going to be 0. See, we don't discuss much regarding to the shear stress in this topic. That is a separate topic would be there. Here, our main point is vertical, not shear. Vertical, not the shear. Shear means along the plane. Vertical means perpendicular to the plane. So don't worry about this one. But as we are discussing over here, then we are going to find out. So from for figure, r is equals to root of x square plus y square. And when below the point load r is equals to 0, I hope you understood why I have taken r is equals to 0 over here. See, I said you for a given Q nana, whatever the load I applied, that's a column load. Due to that load, the stress is going to be a function of here. So now let's take the same thing. As I told you, for a given Q, means whatever the load, this sigma z is a function of r comma z. The sigma z is a function of r comma z. So now from this equation, what I do is, if you observe, see, I'll take a small example. You please observe this example. Let's say that x into y is equals to 10. Let's say x into y is equals to 10. Okay. And this 10 is a function of x comma y. Can I write this one? Let's say how many variables are there here? How many variables are here? 2 variables. So 2 variables. Let's say x comma y is equals to 10. And this 10 is a function of x comma y. So now, how many possibilities of x comma y to get 10? The possibilities are x can be 2, y can be 5. So 2 5 is 10. X can be 5, y can be 2. X can be 2.5, y can be 4. X can be 4, y can be 2.5. And x can be 3.33 and y can be 3.33. X can be 1 by 10 and y can be 10. See, there are n number of possibilities are going to be there. You please observe. See, this is just an example for the sake of explanation. I'm going to tell you. Arey Baba, this Q is not depend upon the R comma Z. This Q is due to column load. So I am going to take, I'm assuming that I'm telling you that some 1000 kilonewtons of the load is applied on the ground level. Some 1000 kilonewtons of the load is applied on the ground level. This stress at any depth below the ground level depends on the radial distance and the depth at which you are going to find out. So now, see, this x comma y is a function of 10. Means x into y is going to be 10. And I can write 10 is a function of x comma y. So when I say 10 is a function of x comma y, for same 10, how many different possibilities are there? X can be 2, y can be 5. X can be 5, y can be 2. X can be 2.4, y can be 4. And you can go for n number of possibilities. Yes or no? And now, can I say, with this point, with this example, when a variable is a function of 2 or more variables, when a variable here 10 is a function of 2 or more variables, for different x comma y values, you may attain the same sigma z. You may attain the same 10 value. I hope you understood this one. Now, see, yet z is equals to 0, it is not going to be possible. These are conditions. Yes, some of our students are, what happens when z equals to 0? At z equals to 0, the load is going to be a point load acting over there. Then the stress is going to be loaded by area. That's it. So this Bosni's theory is going to be at some depth below the ground level. If z equals to 0, then sigma z is equals to be infinity according to the Bosni's. So this theory is not applicable to find out the stress at the ground level. Sir, your audio is not clear. So does my audio is clear? Yes or no? From where 10 comma? Are baba, I took this as an example, Nana. I took this as an example. I said that if I say for, let's say, x comma x into y is equals to 10, then this 10 is a function of x comma y. For different possibilities of x comma y, I can say the same value is going to be present. So similarly, what I am going to do over here is, now if you observe, look, same way, sigma z is a function of r comma z. So now I can write for different r comma z values, there is a possibility of same sigma z. Just say x into y is equals to 10, x2 y5, y2 x5. So different values of x comma y, but you are attaining the same sigma z r naught, means same value. So for different r comma z values, there is a possibility of same. I did not said everywhere the sigma z is same. There is a possibility of same sigma z. Now, if I take all those points into the consideration, if I take all those points into the consideration, okay. Now let's see. Okay. So let's draw the ground level. So this is a ground level. Now again, here this is going to be a point load. For a given load Q, I can take a different points. You can see, you observe over here, I can take this point as R, I can take here, or I can take here, or I can take here. R value is going to be changes or not. Now, you observe, for a different R comma Z. See, for example, I take the point over here. This is going to be the Z and this is going to be the R. Yes. And I take some point over here. This is going to be the Z and this is going to be the R, because this is symmetrical axis R not. Yes. This is going to be the R. So you take any point, from that point of load to the point of consideration, find out the R value. So whatever the R value you see here, this R value, whatever this R value is there, that R value must be there for different R comma Z values. For different R comma Z values, I may end up with the same sigma Z. So now let's take I'm going to have some points over here which are going to be having the same stresses. So these points represents a different R comma Z values, Nana. R would be there and Z would be there. You see, if I ask you exactly below the point of application, this is a point load, this is a point, then what is the value of R here? 0. Here R value is going to be 0. So for different R comma Z values, I may end up with the same stresses. Now, if I join all those lines, observe. If I join all those lines, then I am going to get a line is known as this line is known as isobar. What is this? Isobar. This is known as isobar. Sir, what is this isobar, sir? Isobar means iso same. Bar means pressure. See the unit of a pressure, atmospheric pressure, what it means generally the unit of the pressure, you can represent it in terms of bars, right? Isobar means the same pressures, which means the line joining same stress or pressure intensities. See, on this line, you take at different points. See, this is a different point, this is a different point, and at different points, you can see the R comma Z value. This is a R1 comma Z1, I can say. This is R2 comma Z2, I can say. For different values, I am going to get down the same stress. See, on this line everywhere, the stress is going to be same. It's just like a contour. I hope you know the meaning of contour. Contour means the line joining equal intervals, which means it may be equal stresses or equal time or equal distance or anything, equal intervals, we are going to call it as a contour. So that contour is known as isobar. So the meaning of this isobar is any point you take here, the stress is going to be same. The stress is going to be same. Now, similarly, this is one more isobar. This is one more isobar. And this is also going to be one more isobar. See, for different stresses, different isobars would be there. So for different stresses, different isobars would be there. So for different R comma Z values, there is a possibility of same sigma Z, and the line joining the same stress or pressure intensities are known as isobars. Now my question for you is, out of all these pressure bulbs, which pressure bulb has more stress intensity? Don't you think this is going to be having this one, this one, this one? All these isobars has a same pressure. Don't you think that? Which one has more pressure? Please let me know that. Which one has more pressure? So the isobar near to the load or far away for the load? Near or far? I am asking you the isobar near and far. Which one has more pressure intensity? Near or far? Yes. So it is a near. So you stop. Okay, fine. I got the answers. A lot of answers were there. So whatever the isobar which is near to the load, that will be having a more pressure intensities compared to the far. Stop, 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 stop your answers. Yes. So now, whatever the pressure, let's take due to this load Q, the pressure is equals to Q by area of footing. Okay, Q by area of footing. And then due to this, see at this point, by the time you come over here, at this point, let's say this is going to be 0.8 Q. Let's say, see, I am saying, let's say, I'm telling you again, let's say, don't ask me, sir, how this point came and all those things. Now, you see, by this, at this point, what is the stress you are going to see? At the point load, whatever the stress you are going to see is the area of footing. Let's say, see, the near one has a more stress and the far one has a less stress. So now you observe carefully here, what I'm going to show you is, let's say this is 0.8 Q. What is the meaning of 0.8 Q? By that time, as the distance increases and radial distance is going to be there, this is a Z and this is a radial distance, then some of the stress will decreases or not? Yes, 0.8 Q. And as you go deeper, the radial distance increases and depth is also going to be increases. Let's say this is 0.5 Q. Let's say this is 0.5 Q. And let's say this is going to be 0.25 Q. And let's say this is going to be 0.1 Q. See, what I want to show here is, I am showing you different pressure bulbs. So you can take any value. You can take any value. I can take 0.8. If you want to take 0.9 also fine. So these are the pressure bulbs. And as the depth increases, this is the depth. And as the radial distance increases and depth is going to be increases, the stress is going to be decreases, and the last one is going to be 0.1 Q isobar. Sir, what happened? What is the meaning of 0.1 Q isobar? 0.1 Q means whatever the stress applied over here, which is nothing but Q, and 10% of the stress that is going to be 0.1 Q. So now, whatever the soil mass, now you see from this figure, I'm going to draw one more thing. This is the ground level. From the figure, whatever the pressure bulb, let's say, see, this is a load only Q, and this is going to be 0.1 Q isobar. Whatever this line is going to be 0.1 Q isobar. And now let's say this 0.1 Q isobar, whatever the soil present over here is known as a pressure bulb. So what is a pressure bulb, sir? Pressure bulb means whatever the soil present inside of the 0.1 Q isobar. See, isobar means line joining same pressure intensity. Now let's say the least pressure is going to be 0.1 Q, and whatever the soil present inside of that, see, this entire soil is known as pressure bulb. So what is a pressure bulb, sir? What is pressure bulb? Pressure bulb means soil present inside 0.1 Q isobar is known as pressure bulb. And what happens is beyond 0.1 Q isobar, sir? Beyond 0.1 Q isobar, the effect of external load on soil is neglected. So which means we do take care up to whom? We do take care up to pressure bulb only, which means we do take care only 0.1 Q isobar. We don't go for beyond 0.1 Q isobar. So whatever this soil mass is independent of this load. The effect of this load on this soil mass is neglected. So this is the meaning of the pressure bulb. And what is the meaning of 0.1 Q isobar? So these are the different type of isobars, and the minimum isobar we are going to take is 0.1 Q isobar, and whatever the soil present in the pressure bulb, whatever the soil present in the 0.1 Q isobar is known as a pressure bulb. So now you see that generally for footings, the depth of pressure bulb is 1.5 to 2 times of width of footing. 1.5 to 2 times of width of footing. So what is the meaning of this one, sir? Now you see. Now let's say this is a footing. This is the ground level. So here it is going to be the ground level, and let's say width of the footing is going to be B, and the load passing through the column as a Q in terms of kilonewtons. So where width is going to be the B, and now whatever the stress transferred at the base, let's take it as a Q. What is Q? Q is equals to load by area of footing. And now this B means width of the plate, width of the footing. So now you see below this footing, see if this is the width of the footing B, where B is width of footing. Now below this there is a pressure bulb, and that pressure bulb so this is going to be the pressure bulb. This is going to be the pressure bulb, and whatever the depth up to which this pressure bulb present, whatever the depth up to which this pressure bulb exists over here is 1.52 2 times of width, and this is known as a depth of exploration. What do you call? This is known as a depth of exploration. So DE, where DE is depth of exploration or depth of pressure bulb. Some of the students were asking, sir, up to what depth we have to take the soil mass for the experimental purpose, sir? Sir, you have to take the soil mass in this pressure bulb only, which means beneath the footing, whatever the depth, 1.5 to 2 times of the width of the footing, beneath that only you have to find out the, means you have to excavate the soil and you have to take that soil and you need to conduct the experiments. So, and what is the purpose and shape of the pressure bulb, sir? The shape of pressure bulb is lemniscate shape. There is a lemniscate shape. So what is the shape of a lemniscate means? Example, you can take it as an onion. See, what I am showing you is just a 2-dimension. I am showing you only section view. Okay. So I hope everybody observed onion. And if you cut down the onion, if you cut down an onion, then you can see layers can be seen or not. Those layers are going to be just looks like this isobars. If you see the onion, now I can show you that onion also. I mean, I have to go. I hope everybody has seen that onion. So whatever the shape of onion in 3 dimension, if you take that tip, if you take the tip of the onion, so how does the shape of the onion looks like? That is known as a lemniscate. See, this is not 2D, this is a 3D, but we cannot represent the 3 dimensions over the board. That's the reason why I'm telling you, just imagine the shape of the onion. And if you cut down the cross section of an onion, you can see the layers. That layers are going to be the isobars. So that's the shape of the pressure bulb. And so what is the small q's are? Small q's are load by area, sir. These pressures are, Q is a pressure intensity. Q is going to be Q by capital Q by area of footing. So now, okay. Now, what is the significance of the pressure bulb? Significance. Pressure bulb is used in finding settlement calculations, in finding settlement and bearing capacity calculations. See, we are going to see it in the further chapters. Settlement. See, I am going to find out the settlement in this pressure bulb zone only, and we are going to find out the bearing capacity also in this zone only. So, how to find out the settlement and bearing capacity will be seen in the further chapters. The significance of this pressure bulb. Now, so okay, fine. Now you see, I have given you how to determine the stresses. How to determine the stresses. So if you observe, these stresses are sigma 2 means sigma z. This and now I need to find out how these stresses are going to be varies. Stress variation. Stress variation. You see, Here it is going to be a ground level. Now, you know that this is nothing but a pressure bulb over here. So now if I apply this load Q, I need to know, see, this entire soil mass is under a pressure. Yes or no? This entire soil mass is under a pressure and the minimum pressure is going to be 0.1. So this is a zone where you are going to see the 0.1 Q, but inside stress would be more than 0.1 Q also. So now my question is, as a sigma z is going to be a function of r comma z, as sigma z is going to be a function of r comma z, so you know that as sigma z is a function of r comma z, if I want to study the variations, I have to keep one thing as a constant. I have to keep one thing as a constant, which means either r should be constant or z should be constant. Now see how these stresses are going to be varies. How these stresses are going to be varies. So first of all, if I take z as constant, if I take z as a constant, you see, if I take z as a constant, which means at a particular depth. This is at a particular depth. And does this just looks like a horizontal plane? Yes. So what I'm going to do is I keep z as a constant. When I keep z as a constant, this dotted line is a horizontal plane where you see this is a point, and just below the point, what is this r value here? Here the r value is going to be 0 because r means radial distance. Point load and point of consideration both are same. Then what is r value? R is equals to 0. Now as you go this side, or as you go this side, the r value is going to be increases or not? Yes or no? Yes. So when the r value increases, what happens to the stress? Number one, horizontal plane by keeping z as a constant. By keeping z as a constant. And number two, this is a vertical plane. This is a vertical plane by keeping r is equals to 0. This is a vertical plane. What is the meaning of a vertical plane over here? I take different depth. At this 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, but I am taking everything below the what? Below the point load only, which means I am taking radial distance as 0 and I am varying the z. When you vary the z by keeping r as constant, vertical plane. When you constant z and r is going to be varies, horizontal plane. So this is plane number 1 and this is plane number 2, and there is one more plane. That plane is, you see, this is also a vertical plane, but with a constant radial distance r. With a constant radial distance r. So how many planes are there here? 3 planes are there. So now let's see how the stresses are going to be varies on 1, 2, and 3. So how these planes are going to be varies on 1, 2, and 3. Number 1, stress vertical stress variation on horizontal plane. On horizontal plane. So now you see again, let's draw the this is a ground level. When I say horizontal plane, z is constant, which means at a particular depth, this is at a particular depth. So now, if this is the load Q, and what is this point? This point is going to be R is equals to 0, and here R increases, and here also R is going to be increases. So at this point R is equals to 0. Now let's go for the equation. What is the equation? Can you please tell me the equation once again? Sigma Z is equals to 3 by 2 pi into Q by Z square into 1 by 1 plus R by Z whole square equal to the power of 5 by 2. Everybody have a look. Now I kept which one as constant? You see what is the constant over here? Z constant. Z constant and Z constant, then sigma Z is inversely proportional to R. Sigma Z is inversely proportional to R. You please observe carefully. When Z is going to be constant, then sigma Z is inversely proportional to R naught, because R is in the denominator. Sigma Z is inversely proportional to R, which means at this point when R is equal to 0, the stress is going to be more. When R value increases, then stress value decreases. As the radial distance increases, the stress is going to be decreases. With this point only I started this chapter. As the radial distance increases, then the stress is going to be decreases. Now you see this equation. If you want to go for this one again, as R value is inversely proportional to sigma Z. When R value increases, sigma Z decreases. So now I'm showing you this is a vertical stress, and which is a sigma Z at this point. Now as the R value is going to be increases, now you see what is going to be happen to the vertical stress. See, I am showing you the magnitudes over here. Whatever this arrow mark, this represents the maximum stress at R equals to 0. This is a point of application. Just below that R is equals to 0. And this is going to be R value is going to be increases in both the directions. Now, if you observe at this point R0, stress is more. Now, as the radial distance increases, see from here, as the radial distance increases, the stress decreases. So I am showing you with this arrow mark symbols. This is the maximum, and it is going to be decreases. Now, if I join all those points, how the stresses are going to be varies is. Yes. This is the vertical stress variation. This is the vertical stress variation. You see, this is sigma Z the maximum. Can I say the maximum vertical stress at a particular depth is located when R is equals to 0, and as the depth is going to be increases in both directions, then the value of the sigma Z is going to be decreases. This is a sigma Z, and this is also going to be sigma Z. So these are the variation of vertical stress on the horizontal plane. So I hope you understood. What I have done is simply I kept Z as constant, and R is going to be variable. As sigma Z is inversely proportional to R, as sigma Z is inversely proportional to R, as radial distance increases, vertical stress is going to be decreases. Array, it's not radius, it's the radial distance. When radial distance is 0, see what is the meaning of radial distance first of all? What is the meaning of radial distance? Tell me. The meaning of radial distance is if it is a load, Q, I'm just writing over here, if it's a load Q, the radial distance means, for example, if I take this is a radial distance, then it's going to be X at this point. If I take this point, then what is the radial distance? Y. And if I take this point, then what is the radial distance over here? Root of X square plus Y square. And if I take the section over here, if I take this is a radial distance, then what is R value? R value is going to be 0. So R is the radial distance, radial, in radial directions, in all the radial directions. From here, you observe, I hope. Now, where is this? You see, this is a point load. This is a point load. I hope you can observe. This is a point load, and I want to find out the stress at this section. Whatever the radial distance is, the distance between these two. And if I ask you the point just below the application of the load, then is there any horizontal distance over here? No. The horizontal distance is going to be 0 because they are vertically in the same plane, right? Then the radial distance is going to be 0. Now, please go through this one once again. Okay. For better understanding, I'm telling you in a plan view. In the plan view, you see, this is a footing of width B, and whatever this is nothing but the column. Now, in the section view, in the section view, this is going to be a footing. So now you observe here, this is a ground level, and now if a point load is acting over here, means a load of Q is acting over here. So now if you observe, if I ask you to find out the stress, directly below at a particular depth. See, this is a load, right? Directly below at a particular depth. Then I want to find out the vertical stress over here. See, in the top view, whatever the point and whatever the column load, both are going to be in the same plane or not? As everything is in the same plane, what is the radial distance over here? 0. So just below point load, radial distance R is equals to 0. But now, if I ask you to find out the stress at this corner, see, this is the corner or not? This is a plan view and this is a section view. Now, this is the corner. And at this corner, at a particular depth. Now, if I want to find out a vertical stress over here, Let's take this is Z1 and this is Z2. Now what is the radial distance you are going to see? Now you see this is the load and this is the point where we need to find out. See, for sigma Z1 we can see R is equals to 0. Now what is the radial distance over here? The radial distance is going to be this one. So for sigma Z2 R value is equals to, let's say this is X, let's say this is X, this is Y. What is R value? Root of X square plus Y square. So I hope you understood. See, for the sigma Z1, for finding sigma Z1, as I am asking just below, the point, see, this is the point where we need to find out, and the black point represents the point load. Both are going to be coincide. So in the case of the case 1, just below point load, R value is going to be 0 because there is no radial distance. But as this point over here, there is a radial distance. If this is a point, these are going to be the radial distance. And now, what if both the points are going to be overlapping on the same way? What if both points are going to be overlap? Then R is equals to 0. If this is a black point, this is a red point, and this is the point where I need to find out, then whatever the distance from here to here is known as radial distance. And if I say this black point is exactly locating on the red point, then what is R value? 0. So if you still don't understand, then that's up to you, because I have made sure these conditions. Sir, for example, if I ask you to find out at this point, sir, now you please tell me, sir, for example, if I ask at this point, sir, at this point, then what is the radial distance over here? Y. At this point, what is the radial distance over here? R. And at this point, what is the radial distance over here? X. So the radial distance means from the point of load, means a point load to the point where we are going to find out the stress. And if I want to find out the stress at this point below Z, then the radial distance is going to be X. So now I hope you understood this. No, we don't take eccentricity because whatever the load we are taking is a concentrated load, so we don't deal with the eccentric loads. So that's what Bosniak theory says. He says only the concentrated loads, not the eccentric loads. So now you see, Nana. Now second one is vertical stress on vertical plane. Vertical stress on vertical plane. You see the second one, I am telling you, vertical stress on a vertical plane below point load. See, if I take a plane below the point load, now just now I told you, over here. So now below the point load, this is a point load Q. I want to find out the stresses. This is a vertical plane below the point Q. So now you see here, which is going to be changes, depth changes. But as the point means this is a point load, and where I want to find out the point, either here or here or here. As every point is going to be overlap, then where comes the radial distance? The radial direction is going to be 0. The radial direction is going to be 0. So if this is a load, if this is a point, then this is the radial distance. If point and load where I want to find out, both are going to be coincide, then where is the radial distance? There is no radial distance. Here, this plane R is equals to 0. So now let's see how the stresses are going to be various. See, you know that when R is equals to 0, sigma z is equals to 0.477 into Q by Z square, which means can I write sigma z is inversely proportional to Z square or not? Sigma z is inversely proportional to Z square, which means as Z increases, sigma z decreases and varies non-linear or curvy linear, because it is a square or this is a square or normal, means is it z or z square? If it is z, it varies linearly, and as it is z square, it is going to be parabolic or non-linear. So now what I am going to take here is, this is a sigma z. See, don't think this is a horizontal stress. That is the magnitude of vertical stress. At this particular depth, the vertical stress is going to be more. At this particular depth, the vertical stress decreases, and as you go on, the vertical stress decreases. Now you tell me, as a z increases, the sigma z decreases. So at lesser depth, the value is going to be more. So at this point, the sigma z is going to be more, and at this point the sigma z is going to be less, and at this point the sigma z is going to be much lesser. So now if you observe, by joining all these points, if I draw the variation will be looks like the parabolic variation, and mind it, they won't touch together. When they will touch, you see, observe, when z is equals to infinity, then only vertical stress is going to be 0. It is not going to be possible. And you see here, they won't touch. See, this variation will not touch either x-axis or y-axis. So now, whatever the representation I am showing you here, at this one, you see, this is the magnitude of vertical stress at a particular depth, Z1. This is the magnitude of the vertical stress at a depth Z2. This is the magnitude of the vertical stress at a depth Z3. So here, this is the variation of the vertical stress, means as a depth increases, you see the magnitudes of sigma z, they are going to be decreases. So this is how the variation is going to be looks like when the vertical stress on vertical plane below the point load. So sigma z is inversely proportional to z square, and as a depth increases, sigma z decreases. Now, okay. One minute, I will check. Internet connection is also good. Then why you people are getting this many problems? Okay, fine. So now let's see the last one. Third one, vertical stress variation on vertical plane with r greater than 0. See, this is with r is equals to 0. This is with r is equals to 0. Now, I take a vertical plane. This time also I take a vertical plane only. So this is a ground level. And now let's say this is a point load which is going to be Q. But this time I'm going to take at some radial distance. Let's say this is a radial distance R1. So now on this plane I'm going to take the vertical plane. Here you see this is the variation I'm going to discuss now. Yes. So now if you observe here, find out write down the equation once again. 3 by 2 pi into q by z square into 1 by 1 plus r by z whole square whole to the power of 5 by 2. Now can I write this equation as 3 by 2 pi into q by z square into z square by r square plus z square whole to the power of 5 by 2. Yes, I can write down this equation like this. Yes, yes or no? Because you see, observe. Now you observe z square whole to the power of 5 by 2. What is this value? Z square whole to the power of 5 by 2. What is this value? Z to the power of 5. This is z to the power of 5 and z to the power of 5 and z square. So now finally it is going to be 3 by 2 pi into q into z to the power of 3 by r square plus z square whole to the power of 5 by 2. See, why I made this equation is, see, while I am calculating, I use this equation only. But I made this equation to this form. Now, what I want to show here is, now you tell me, does sigma z, does r value is 0? No. R value is not going to be 0. So now you see, there is a z in the numerator, there is a z in the denominator. There is a z in the numerator and there is a z in the denominator. See, the sigma z has a numerator z and a denominator z. So when the z is going to be present in both the numerator and denominator, can we say directly the stress is going to be varies? Can we say directly the stress is going to be varies? No, we cannot say directly the stress is going to be varies, because as the z is going to be present on the numerator and the denominator, you cannot say directly whether the stress increases or decreases. So as numerator and denominator is there, it can be increasing and decreasing, and it can be decreasing and increasing. So it was observed for this plane, especially in the case of the vertical stress variation. So in this case, vertical stress increases at first and then decreases. Sir, why it is going to be happen like this, sir? Sir, if you please observe this equation, sigma z is directly proportional to, if you have any doubt, you please refer this equation. So sigma z directly proportional to z cube by r square plus z square put to the power of 5 by 2. As z is present in the numerator and in the denominator, at first it is going to be increases and then it is going to be decreases. At first it is going to be increases and then it is going to be decreases. So now at first the stress is going to be increase and then it is going to be decrease. You see, at first the stress is going to be increases and then it is going to be decreases. See, whatever the representation I am showing you here, this is the at first the stress increases and then decreases. So this is sigma z maximum. And you know, whatever, this is nothing but the vertical stress only. Don't think this is a horizontal stress. So that is sigma z maximum. Okay. Now, what I do is, for better understanding, I'll go for one more R value, R2 value, R2 value. So what I do is here, now if you see, as you increase the R value, you observe here, now at the same depth, let's take, at this depth, at radial distance R1, at radial distance R1, see at this depth, this is the depth, right? At the depth, at radial distance R1, I get some sigma z. Now, as I increase the radial distance at the same depth, the stress is going to be decreases or not? Yes or no? Observe clearly. Now I am taking z as constant. If I keep the z value same, now for R1 and R2, for R1, sigma z is more. As R2 increases, sigma z is going to be decreases. So at the same depth on this plane, the stress is not a maximum. So here what is going to be happen, sir, means here what is going to be happens over here is you observe, okay, sorry. So at this point, now, if you understand it clearly, see in this zone, what happens over here is, now the stress is going to be decreases and becomes maximum. Maximum and then decreases. You see here, this is the maximum stress point over here. This is the maximum stress over here. See, as the radial distance increases, what is going to be happen is the stress is going to be shifts. This is a stress diagram will shift from this position to this position. And as you go beyond this point, again the stress distribution is going to be shift. Why, sir? Sir, as radial distance increases, the vertical stress decreases further, sir. So the entire stress distribution is going to be decreases. Yet first on this plane, why the stress increases and decreases is due to variation of z in numerator and denominator. Second point, Why the stress is shifting downward means as the radial distance increases, stress will decreases. So from the observations, you see for anything to be maximum, to be max, its slope should be 0. Slope should be 0. So for sigma z to be sigma z max, you see these points are sigma z max. Is going to be 0, then whatever the value, this value you see, this beta, then beta becomes 39 degrees 15 minutes. See, you don't need to worry about what is the value over here. You don't need to worry about here. You please observe. So one thing for sure over here. See, so 1 o'clock. Okay, fine. With this I'll stop. With this I'll stop. So the angle made by plane passing through maximum vertical stress is 39 degrees 15 minutes. So this is how the variation of the vertical stress looks like. In the case of the vertical stress variation on vertical plane with R is going to be greater than 0. So now that's all with this one. So what about now? Still is a problem. Okay, fine. I'll be stopping. See, there is no derivation. I'm not. I'm not discussing any derivation over here. There is no formula for the value. See, there is no formula for this value. You see, if you solve this equation, whatever this equation is there or not. So if you derive the slope, you so from the mathematics concepts, Anna, when you want to make sure anything maximum or minimum, its slope should be 0. So now I'm not going to give any derivation. The derivation is not important. If you solve this one, you are going to end up this beta value as 39 degrees 15 minutes. So you please remember that value. Don't need to go for anything else. The point that you need to know in this entire slide is, see, when there is a vertical stress variation on vertical plane, first the vertical stress increases and then decreases. Okay. And as the radial distance increases, this vertical plane will shift downward. And if I draw a line by joining the maximum points here, this line will make an angle of beta with respect to vertical. And what is that beta? Beta is going to be 39 degrees 15 minutes with vertical. That's it. You don't need to go too much into this one. I'm not giving any derivation. There is no derivation for this. So you don't worry about the derivation. Okay, so with this, I'm stopping this session. With this, we have completed the Bosnisk theory, Bosnisk point load theory. We'll solve the problems tomorrow. but as a lot of the people are saying, they're getting some difference. Okay, fine. Okay, we'll stop the class session now. Okay, so I'll stop the session now, but I'll be taking a quick revision. So today's we have been discussed about these things regarding to the stress due to self weights, means stress due to external loads. You please go through this one. Tomorrow we'll be discussing the remaining things. Okay, fine. So those who wants to leave, they can leave. And now I am going to give a quick review of the previous sessions that we have been discussed. So now, earlier, let's go for the, give me a minute. I will open all the PDFs that I have shared with you. Just give me a minute. Yes. So okay, fine. So that's all about this. You please go through the today's class. So once you go through the today's class, then you can understand much more better. Okay, fine. Let's start a quick revision about the concepts that we have been discussed in earlier classes. So, is that, yeah. So this is the point where we have started the permeability chapter. So in this permeability chapter, first of all, we have been discussed about the definition of permeability, the ability of a soil to permit the water. So whenever there is a ability, then you need to find out that ability, and whatever the flow of water through the soil is nothing but a seepage, and this seepage will take place. So you see, observe over here. So this seepage requires some energy. That's first I took an example. So for initially you have some 500 calories and then 100 calories. What is the energy you required? 400. So what is the minimum energy required you to move for 1 kilometer is 400. That is nothing but the hydraulic head. So hydraulic head is a H is a difference between the water levels, which is the minimum energy required to cause a flow, or the net head required to cause the flow. And from the Bernoulli's principle, I said you the velocity head, as the velocity of flow in the soil is very less, we neglect the velocity head. So in soil, total head is nothing but pressure head plus datum head. And then we discussed about this hydraulic gradient line. So wherever you want to find out the pressure head, you need to use which device? Piezometer. So what is a hydraulic gradient? Hydraulic gradient means head loss per unit length. So what is a head loss, sir? Or hydraulic head, which is the difference between the water levels per unit length. So the physical meaning of head loss is fall of water level. And as you see, the slope of hydraulic gradient is head loss per unit length. I is equals to H by L. Wherever you want to find out the head loss, Hx is equals to I into length up to x. So we can use this equation. So the important things here is the definition of the hydraulic head and the total head, and what is the hydraulic gradient line, and how to determine the head loss at any section. So this is one of the example that I have taken, and these questions we have been discussed thoroughly in chapter number 8 and in chapter number 8. So wherever we want to find out, the stresses, wherever we want to find out the pressure, you please insert the piezometer, you know that. So always flow occurs from higher energy level to lower energy level. So please keep in your mind, whatever the total seepage length you find out and whatever the head you find out, the step 1 is going to be to find out the hydraulic gradient. See, I have given you the following steps over here. You please go through these steps also. I mentioned you these steps. You see, I hope you have been going through these steps also. Whenever you want to find out the pressure head, you need to follow these steps. These steps are very, very important. Step number 1 is going to be to find out the hydraulic gradient. Step number 2, to find out the head loss at any section, Hx. And step number 3, insert piezometer and find out the pressure head. So these are the 3 steps that have been included, and we have been discussed about these things earlier. Now, and then we saw some questions regarding to the how to determine the head loss at any section. So I have provided some points over here. Then we discussed about the Darcy's law. So in this, up to this point, the point you need to remember out of all those in the first one is these 3 topics. Step 1, step 2, step 3. How to find out hydraulic gradient, how to find out head loss at any section, how to find out the pressure head at any section. Now, and then we discussed about the Darcy's law. According to Darcy, V equals to Ki, where V is the Darcian velocity or discharge velocity, K is the quotient of permeability, V directly proportional to I. And based upon that, we can say a soil is highly permeable when K greater than 10 to the power of -1 centimeters per second, and impermeable when K less than 10 to the power of -7 centimeters per second. And as the validity is going to be, so flow should be laminar and Reynolds number should be less than 1, and it should happen only in the fine sands and silts, not on the coarse sand or gravel. So these are the Reynolds number I have given for different type of flows also. And in the case of gravels, the velocity is not going to be directly proportional to I, means it's not linear. It's some value of x, that x is going to be 0.65 for turbulent flow. And then seepage velocity, as we know, the area is not a correct area, so the velocity is not going to be a correct velocity. So the discharge velocity is not a true velocity, it is a superficial velocity. The seepage velocity is the actual flow velocity, whereas the seepage velocity Vs is equals to V by M. So seepage velocity is equals to discharge velocity per unit velocity, and always the seepage velocity is more than the discharge velocity. And then we discuss the quotient of percolation. Then we discuss the flow analysis when the anisotropic soil mass. In the case of the anisotropic soil mass, when our flow is parallel to bedding planes and when our flow is perpendicular to bedding planes. So you need to remember one thing over here. When the flow is parallel to bedding planes, you know that discharge is going to be same. So Kx is going to be weighted average. When the discharge is going to, when the flow is going to be perpendicular to bedding planes, now using this condition, when the flow is perpendicular to the bedding planes, this is going to be similar to pipes connected in series. See, this is very, very, very important. Here, the logic is all the velocities are same, which means the product of K into I is going to be same. So Ky into I is equals to K1 I1 is equals to K2 I2. So then from this we can find out Ky is equals to Z1 plus Z2, sigma Z by K. So in the case of the gate examination, I hope you people have gone through the previous gate questions and you know how many questions have been asked on the anisotropic soil masses. So they have asked the questions, what is the ratio of Kx to Ky? They have been asked to find out the vertical permeability. They find out the horizontal permeability. So this topic is a really, really hot topic in this chapter. Very, very important topic. So for that, based upon that, I have explained some of the gate questions in this one. So you please go through these gate questions, every question, and I have explained the logics also here, how to determine all those things. And this is one of the previous gate question where the flow is perpendicular bedding plane, how to go this one and this one. So you please go through the notes once again. Then we discussed about the experimental procedures. Out of those, we need to worry about the constant permeability test and falling head permeability test. In the case of constant head permeability test, we are going to supply the water continuously so that the difference in the water levels is going to be same. And at the end, we are going to collect a volume of water in this jar per unit time, which is nothing but discharge is equals to volume of water by time. So with this, we can find out Q is equals to KIA, and then we can find out, means from this one, we can say this test is not suitable for the fine grained soil because it takes long time. In the case of falling head permeability test, as you supply the water only once, now note down the time that required to fall the head from H1 to H2. And if you apply this equation, you will be ending the equation as K is equals to A into Z by capital A into T into log base H1 by H2, where T is the time required to drop the H from H1 to H2. Now next I discussed about a condition. If the time required to fall the drop, means to drop the head from H1 to H2 and H2 to H3 are same, which means H1 to H2 and H2 to H3 are same, then what is the relation between the H1, H2, H3? I hope you have seen the previous ES equation also. So H2 is equals to root of H1 into H3. And then we discussed about the factors affecting permeability. From this, I said you as a particle size is more, permeability is more, and you need to remember this equation, empirical relations. So according to Allen Hagen, K is equals to 100 into D10 square, then D10 centimeters, K also centimeters per second. And if it is in a mm, then see 750, if they give 750, then D10 is going to be mm and K is going to be meters per second. So then we discussed about the void ratio, K directly proportional to EQ by 1 plus C. And then we discussed about the fluid property. As temperature increases, viscosity increases, permeability increases. So we have solved some questions regarding to all these things. And degree of saturation, entrapped air offers resistance, organic matter finer the soil, lesser the permeability. So that's all about the permeability chapter. In this chapter, for the examination of point of view, what you need to remember is, see, wherever there is a flow passing through the soil, Darcy Aya, Q Kia. Darcy Aya, Q Kia. That's it. Q is equals to KIA. Wherever there is a flow, you apply that equation, Q is equals to KIA, where I is hydraulic gradient. How to find out hydraulic gradient? Difference between water levels by seepage length. And mind it, if it is a horizontal seepage, length is horizontal length. If it is a vertical seepage, length is depth of the soil. If it is an inclined seepage, you have to take the inclined length. So this one I have given one of the example also. In this question, they mentioned L as 40, but as it is inclined seepage, we have taken it as a L dash. So I hope you people have gone through this PDF also. That's about the chapter number 6 of permeability. So there we discussed the two topics. One is a hydraulic gradient, other one is a discharge. That's it. Now coming to the 7th chapter, effective stress. In the case of the effective stress, and in the case of the effective stress, so if you see here, the stresses within a soil mass at any depth is due to external load applied and self weight. So just now we started chapter number 10, external loads we'll be seeing tomorrow also. And as of now, the self weight of the soil mass, and this self weight of the soil mass, we can also call it as a geostatic stress. So at any depth you want to find out the total stress, just whatever the unit weight above into its depth, whatever the unit weight above into its depth, that is going to be the total stress. So total stress means a total load by area. Wherever you want to find out the total stress, you can see these examples. So here gamma sat into Z, but in this case gamma Z1 plus gamma sat into Z2. And now you see this total stress is going to be a compression of two stresses. One is stress due to water and other stress due to self weight. Whatever the stress due to water is known as pore water pressure, and stress due to self weight is known as effective stress. So what is this pore water pressure? This pore water pressure is a pressure exerted by in pores, and this is going to be same in all the directions. So as it is going to be same in all the directions, it does not cause any compression to the solid. That is the reason why we call this as a neutral stress. And how to determine this pore water pressure? You know that simply pressure head, and you know how to find out the pressure head? Piezometer. As it is a hydrostatic condition, when there is no flow, there is no loss of head. So water level will rise directly to the water table. Keep that in your mind. If there is a flow, there is a head loss. When there is a head loss, there is a fall of water level in the piezometer. No flow, no head loss, no fall of water level. So how to determine the effective stress? As effective stress cannot be measured directly, we can find out effective stress as total stress minus pore water pressure. So the conclusions I am giving you here is these conclusions are very, very important. Above water table, or at a water table, the pressure is going to be zero. Pore water pressure is going to be zero. When pore water pressure is going to be zero, effective stress is equals to total stress. And below water table, always effective stress is less than total stress. Use gamma dash for effective stress. Use gamma sat for total stress. And effective stress is responsible for the engineering behavior. And then from now onwards, from compressibility chapters onwards, we are going to look over those things only. Okay. And then we discussed about the questions, how to determine the effective stress. I have been given these questions, and I explained you the effect of the water tables by taking these examples. You please go through this logic also. So I gave you this logic. See, these logics are very, very important for solving in the examination. Please understand these logics. Whenever no change in the unit weight, no change in total stress. When there is no change in total stress, pore water pressure and effective stress both are same. But as the unit weight is going to be changes, you see, if the water table is going to be get slowed, total stress decreases, pore water pressure decreases, but effective stress is going to be increases. The same way, if water table rises to the ground level, yes. If water table rises to the ground level, then you can observe. Yeah. Then you can observe the change. You can see here water table rises, then total stress, pore water pressure increases, but effective stress decreases. So for all of these things, I have given a conclusions over here. The conclusions are: if water table gets lowered below ground level, total stress, pore water pressure decreases, and effective stress increases, and vice versa when water table rises up to ground level. And if water table rises above ground level or bed level, total stress, pore water pressure increases by same magnitude, and no change in effective stress at any depth below the ground level. So if you want to understand, you please go through this example also. I have shown you in this example, above ground level, the change in effective stress is going to be zero. So fluctuations of water levels in lakes or rivers due to seasonal changes does not cause any change in the effective stress. And then we discussed about the stress variation along the depth. So effect of rainwater is always under saturation because there is no water table, no buoyancy. Similarly, in the case of effect of surcharge, as the effect surcharge is going to be acting all over the surface area, the effect of surcharge is same at any depth with an increase in magnitude of a Q. This is again one more conclusion over here. And then we discussed about this question over here, and then we discussed about different type of waters. Free water. So whatever the soil mass below water table is free water. So far we have been discussed about the groundwater table. And then if some portion of the soil mass, you see, by soil investigation, it was observed that some portion of soil above water table is either partially or completely saturated up to certain height. That is known as zone of capillarity, and the water is known as capillary water. So there is some more water, hygroscopic water and structural water. This effect of hygroscopic and structural water is very, very less. So we don't need to worry about those. And now coming to the effect of capillarity, the effect of capillarity in soils is similar to capillaries in the capillary tube. So now if you insert a capillary tube, due to surface tension, due to surface tension, water level in capillary tube rises up to certain height known as HC, and that HC is equals to 40 cos alpha by gamma W into D, and by taking proper approximations, HC is equals to 0.3 by D, where HC is inversely proportional to D. Lesser the dia of tube, more the capillary rise. Lesser the dia of the tube, more the capillary rise. So surface tension, it is known as a tensile force acting along the surface due to intermolecular forces. Now, in the case of the soils, whatever the dia of the void space is nothing but the capillary tubes. So where D is the dia of the interconnected void spaces, how to find out that dia D is nothing but D is equals to E into D10. And mind it, in this equation, you have to remember HC should be in terms of centimeters and D10 in terms of centimeters. So keep that in your mind. In this chapter, every conclusion is very, 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 very important. They may not be important in this chapter, but they are going to be important in every other chapters. So what happens when water table fluctuate? Below the ground level and above the ground level. And now what happens due to capillarity? So due to this capillary water, as I said, capillary water is under tension. As a soil is good in compression and poor in tension, in soils we take tension as negative. So whatever the pressure exerted by the water due to capillarity is nothing but capillary pressure, which is going to be negative pressure. And you know that clay has a large capillarity, but due to permeability, it takes very, very long time. And then we discussed about the capillarity. You see, I have given over here, as a capillary pore water pressure is negative, then effective stress is going to be increases. So due to capillarity, effective stress increases, and effective stress can be less than or greater than or equals to total stress. And then we discussed about the effect of this capillarity, and I told you, comparing with the capillarity and without capillarity, below water table, I have shown you, you see, below water table, you observe over here, below water table, without capillarity and with capillarity, without capillarity and with capillarity, below water table, the change in pore water pressure is going to be zero. When the change in pore water pressure is going to be zero, the change in effective stress is nothing but change in total stress. Please, people, you need to go through each and every logic over here. If pore water pressure is zero, then change in total effective stress and change in total stress both are same. How to find out change in total stress? Whatever the change in unit weight into capillary rise. So in this equation here, I said you the capillary rise is going to be, so how many meters over here? 2 meters. Initially it was gamma, finally it was 20 minus 80 into 2. Then we discussed about the questions regarding to all these things we have been going through. And you see I have explained all the examples with the logics also. Due to lowering of drainage and capillary saturation, when you lower the water and already it is capillary saturated, then the net unit weight is same, because if there is a water table gamma sat, due to capillary saturation also gamma sat, when there is no change in the unit weight, then there is the change in total stress is zero. When change in total stress is zero, the change in effective stress is equals to minus change in pore water pressure. So as water table lowered, then whatever the decrease in the pore water pressure is equals to increase in the effective stress. I hope you people are able to follow. That's about chapter number 7. And in this chapter number, one more thing. If a soil is filled with any liquid other than fresh water, then you have to include this SL. What is SL over here? Specific gravity of that liquid. So now, and that's about the chapter number 7. And in chapter number 7 only, at the end, we discussed about one more topic. The topic is Artesian condition. You know what is the meaning of Artesian condition? Whenever a confined aquifer means if a permeable layer is present between two impermeable layers, then that is a confined aquifer. In this case, due to this percolating of rainwater, what happens is if you insert a tube well in the confined aquifer, the water level will rise to the corresponding water table, which is more than the water table. This is the water table of the unconfined aquifer. So unconfined aquifer water table is different. Confined aquifer water table is different. If you go for artesian condition, water level rises into this well above the water table. So whenever the water level in the artesian well is more than the water table, then that is known as artesian condition. So due to confinement, water pressure in artesian aquifer is very high and tries to move upward. So now I wrote note points over here. If well is dug into confined aquifer, then water level rises into artesian head, and unconfined aquifer pressure head. So this was the question that we mentioned over there. Now in the case of the chapter number 8, I hope you people are following. Okay. So in the case of chapter number 8, I have explained you what happens to effective stresses when you apply seepage. This is a hydrostatic condition. When there is a hydrostatic condition, no seepage. And in the case of downward seepage, as a seepage acts along the direction of flow. See, I directly go to this condition. You see, yes, seepage pressure exerted by water along the direction of flow. So as a seepage acts along the direction of flow, downward seepage positive, upward seepage negative. So in the case of the downward seepage, effective stress gamma dash into Z plus gamma W into H. Upward seepage gamma dash into Z minus gamma W into H. And the logic I mentioned over here, by comparing 1 and 2, if you see over here, there is no change in the total stress. When there is no change in the total stress, change in effective stress is minus change in the pore water pressure. As water level falls by H, then pore water pressure falls by gamma W into H, and effective stress increases by gamma W into H. So you please go through all these conditions. And in this condition, finally, I apply the logic is, if I ask you a question in the case of downward seepage, you please find out gamma dash into Z, gamma W into H. What is Hx? Head loss of Tx. Just you simply add. And if you see the upward seepage, gamma dash into Zx downward, and gamma W into Hs of x, where Hs of x is a balanced or remaining C by Z at xx. And then we solved the questions. So this is a previous gate question for the downward seepage, and I have given for the upward seepage how to solve all these things with the logics also. Then seepage force per unit volume, which is nothing but gamma W into I, and resultant force is going to be for horizontal seepage root of gamma W into I whole square plus gamma dash into I whole square. And then we discussed about the quicksand condition. What is quicksand condition? Whenever the soil behaves like a liquid, then we are going to call it as a quicksand condition. And where is going to be happen? Upward seepage. When upward pressure is equal to downward pressure. And what type of soils you are going to see? Cohesionless soils. So what happens? The strength becomes 0. And at a critical condition, factor of safety is equals to 1. So what is the factor of safety? Downward pressure by upward pressure. So if you see this one, from this I can find out the critical hydraulic gradient. IC is equals to G minus 1 by 1 plus R, G minus 1 into 1 minus N, and IC is generally is equals to 1, and the factor of safety is equals to IC by I. If a surcharge of intensity Q is applied, then factor of safety is equals to gamma dash into Z plus Q by gamma W into H. Then quicksand is not a type of sand, it's a type of soil mass, and its density is going to be twice as the density of the water. So this about the some of the conditions are regarding to the quicksand condition. And then we discussed about a different type of failures, a piping failure. The backward erosion from the downstream to the upstream due to quicksand condition is known as piping failure. So how we are going to reduce it? By increasing the length and by providing a downstream sheet metal wall and by providing inverted filter. So the specification of the inverted filter is a D15 of filter to D85 of base should be less than 5 to prevent escape of particles. D15 of filter to D15 of base greater than 5 to allow the water to percolate to downstream side. And then we discussed about the quicksand condition over here. See, quicksand condition also occurs when a trench is excavated below water table and made excavation free of water. See, what I do is I simply take at this condition for no failure, effective stress is going to be 0. When effective stress is 0, quicksand condition occurs. Simply find out the total stress, find out the pore water pressure, you equate both. You equate both. So now, yes. So the similar thing, we can see the same type of excavation conditions in the case of artesian case. In artesian case, when total effective stress is equals to 0, total stress is equals to pore water pressure. So total downward pressure is equals to total upward pressure. And then we have solved some questions regarding to all those things. That's with that we have ended the chapter number 8. So these are the chapter number 8 and chapter number 9 we discussed about seepage analysis. Yes, in the case of the seepage analysis we have used the Laplace equation for homogeneous and isotropic soils, and then we discussed about the characteristics of flow net. What are the characteristics of flow nets? Always discharge remains same, Q is equals to NF into delta Q, and delta H is equals to ND into delta H. The only formula that you need to remember throughout here is this formula. Q is equals to K into H into NF by ND. If it is going to be exit gradient, factor of safety is equals to IC by I exit. How to find out I exit? Delta H by delta L of exit. And for the anisotropic soil mass, if you want to apply the fluid characteristics, what you have to do is you must have to go through the nature should converge to equivalent isotropic by reducing the base length of the dam x dash h to x dash. So then the K is going to be Ke root of Kx into Ky. And then we discussed about the remaining things today. So this is just a quick review about the things that we have been done so far. So finally, I want to conclude with 4 formulas. Number 1, hydraulic gradient I is equals to H by L. Hydraulic gradient I is equals to H by L. From that you can find out the head loss at any section. Hx equals to I into length of base. Number 2, wherever you want to find out the discharge, Darcy Q Kia. Q is equals to KIA. And number 3, finding the total stress and effective stress. Wherever you want to find out the total stress, keep your palm above unit weight into depth. And effective stress, total stress minus pore water pressure. And number 4, whenever effective stress becomes 0, then the quicksand condition is going to be occur. And number 5, by using flow net, Q is equals to K into H into NF by ND. See, based upon these 5 points only, almost all the questions are going to be rotated. And now it's up to you. If you practice more and more and more, I'm telling you, you can understand this topic so very, 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 very clearly. So first, you please go through the notes, and I have given you enough number of points through the notes, and I have discussed the previous gate and classroom practice questions. Practice, practice, practice. That's the only one thing that you can do. I hope this is very useful. So I hope it will be useful for all of you. It's already 1:37. Yes, at the end of the all the sessions, I will be taking a quick review of this chapters, all the chapters. So don't worry, I will be taking once again a quick review. So with this, I want to conclude the session, and it's already 1:38. So please explain chapter number 6, assignment question number 6. My dear student, I am going to send you the solutions for the chapter number 6 today. You please look over that, and still if you have any doubt, we can get to that. Thank you all of you. What is drawdown curve? Whatever the hydraulic gradient line is nothing but drawdown curve, Nana. So please upload your short notes of geotech by today. Yes, I will be trying to upload, and yes, I have been some work yesterday and day before yesterday. That's the reason why I did not upload. So today I'll be giving. See, the assignment problems. It's not that easy to prepare, so I have to prepare because I will be preparing always a new type of questions completely continuously. I don't want to follow the same old questions, so that's why it will take time. So I'll be sending you. Don't worry. So for prelims examination for calculations, please say some easy tips to solve. Say I was saying every time while I was calculating, I was saying right. So Mr. Vivek. Okay, fine. As today the time is around 1:40, and I have one more session after 2 o'clock, and I have one more class. So what I do is, please, we'll take the doubts clearing session tomorrow, because with this we have completed all the 9 chapters, right? So what you do is, and whatever the students who are there, I'm going to send you the questions. So please go through those questions, all those questions, and you please try to solve. Still, if you have any doubts, we'll be discussing in our tomorrow session, because as it is 1:40, I have to go and I have to hurry up. So I'm sorry for today. I thought of completing the review within 15 to 20 minutes so that I can take half an hour of doubt session, but it does not happen. But tomorrow we'll definitely take that. So, and still if you have any questions, you please mail to me, and I'll try to respond through my mail. Okay, fine. Now you can leave. Those who wants to leave, you can leave. Even I am also going to leave. So meanwhile, I'll look over the Generally for morning batches, when the syllabus will be complete. See, as now every batch is included, morning and evening, every batch is included. So there is no specification for morning and evening batches now. Yes, do you teach any other subjects? Yes, I do, but I won't say now. We'll be seeing later. I'm a little confused in upward and downward forces, when to take gamma and when to take gamma dash. My dear student, you please go through the notes once again. You try to solve a more number of questions, then you can understand it much more clear. So with this, so have a nice day for all of you, and I'm quitting out of the session. So we'll be meeting again tomorrow.